There is a moment in every scientific field when the impossible becomes real. For centuries, black holes were nothing more than a mathematical ghost, the prediction of a theory so powerful it warped our understanding of reality, yet utterly invisible to our eyes. Then, in April of 2019, that ghost took form. The Event Horizon Telescope project didn't just give us data, it gave us a picture. A fiery, donut-shaped ring of light swirling around an abyss of perfect darkness, a cosmic confirmation that felt less like a discovery and more like a revelation. That single image, the first direct visual evidence of a black hole's shadow, didn't just make headlines, it sent a shockwave through the entire global community of astrophysicists, a collective gasp of awe from the very people who thought they had seen it all. In that moment, they weren't just researchers analyzing photons, they were human beings staring into the profound and beautiful unknown, completely and utterly stunned. This is the true heart of space exploration, the part we so rarely get to see from the outside. We often picture scientists as cool, detached figures in lab coats, methodically checking boxes and confirming hypotheses. But the universe has a wonderful habit of shattering expectations. It hides wonders in the void that defy our most carefully constructed models, presenting puzzles so bizarre and phenomena so magnificent that they leave even the most brilliant minds momentarily speechless. These aren't just minor corrections in a data set. These are the moments where the rulebook gets thrown out the window, where a single observation can overturn decades of consensus and force us to rewrite the textbooks. This is the thrilling, human side of cosmic discovery, the raw, unfiltered reaction to the truly unexpected, and that is the incredible journey we're embarking on today. We are about to count down 25 of the most astonishing, head-scratching, and mind-bending moments in space science, a collection of discoveries so profound they left the experts completely shocked. From rogue planets drifting alone in the interstellar darkness to stars that flicker in ways that seem to defy the laws of physics, we will explore the bizarre and beautiful outliers that have redefined our place in the cosmos. So get ready to peer over the shoulders of the world's top astronomers as we dive into the data that made them do a double take, the signals that no one could explain, and the celestial surprises that prove, once and for all, that the universe is far stranger and more wonderful than we ever dared to imagine. Of course, this kind of profound shock doesn't always come in the form of a stunning visual. Sometimes the most earth-shattering discoveries arrive as a series of numbers and letters printed on a continuous sheet of paper, a pattern so anomalous that it defies all logical, earthly explanation. That is precisely what happened in the late summer of 1977 at the Big Ear Radio Telescope in Delaware, Ohio. It was a project searching for something most astronomers considered a long shot, a signal from an intelligent civilization beyond our own. Night after night, the telescope dutifully scanned the sky, its massive ear listening to the cosmic static, recording the background hum of the universe. The work was methodical, often tedious, with reams of data to be reviewed by hand. Then, on August 15th, volunteer astronomer Jerry Amon was performing his usual review of the previous night's computer printout. The data was typically a chaotic mix of letters and numbers representing signal intensity, mostly ones and twos, the cosmic equivalent of quiet background noise. But as his eyes scanned across the page, he saw a sequence so powerful, so starkly different from everything around it, that it leaped off the paper. The characters 6EQUJ5 blazed from the readout. In the telescope's code, this represented a signal that was 30 times stronger than the ambient noise of deep space. It was a narrowband radio burst, precisely the kind of signal scientists had theorized an advanced civilization might use to broadcast its existence, and it was centered on the hydrogen line frequency of 1420 MHz, a wavelength that many considered a logical, universal channel for communication because hydrogen is the most common element in the cosmos. For 72 seconds, the signal blared, rising and then falling in intensity exactly as you would expect from a celestial source passing through the fixed focus of the Big Ear's observation window. And then it was gone. Eamon, a man of science not prone to dramatic outbursts, was so utterly floored by the sheer perfection and power of this anomaly that he circled the alphanumeric sequence on the printout and, in the margin, simply wrote 3 letters in red pen. Wow, that single human expression of pure, unadulterated astonishment gave the signal its immortal name. The initial shock, however, was quickly followed by a concerted scientific effort to find it again. Teams pointed every available radio dish they could at that same patch of sky in the constellation Sagittarius, listening intently for a repeat, for any hint of another message. But the universe offered only silence. The wow signal was a one-time event, a cosmic shout that has never been heard again. To this day, it remains one of the most compelling mysteries in the search for extraterrestrial intelligence. While some have proposed natural explanations, like a comet's hydrogen cloud or a bizarre form of interstellar interference, none have fully accounted for the signal's unique characteristics, its precise frequency, its powerful strength, and its perfect 72-second duration. Every proposed explanation has a hole, a piece of the puzzle that doesn't quite fit. The wow signal endures not just as a data point, but as a ghost in the machine of astronomy. It's a haunting reminder of a moment when we might have briefly touched something extraordinary, a potential hello from the void that left even the most skeptical researchers asking a thrilling, terrifying, and ultimately unanswerable question. For those 72 seconds, was someone or something actually talking to us? While the wow signal was a fleeting shout from the void, astronomers are sometimes confronted by a much quieter, more persistent kind of mystery, one that whispers in the background for years, subtly challenging our understanding of the fundamental laws that govern motion itself. This was the case with the twin deep space voyagers Pioneer 10 and Pioneer 11. Launched in the early 1970s, these rugged spacecraft were pioneers in the truest sense, the first to venture through the asteroid belt, the first to send back stunning close-up images of Jupiter and Saturn, and the first human-made objects destined to leave our solar system entirely. For decades after their primary missions were complete, scientists continued to track their faint radio signals, using the Deep Space Network to monitor their positions and velocities with incredible precision as they coasted silently into the abyss. It was during this long, quiet vigil that navigators began to notice something deeply peculiar. Both spacecraft, now millions of miles from the Sun and any significant gravitational pull, were not following their predicted path. According to the unshakable laws of Newton and Einstein, their speed should have been virtually constant, with only the faintest, calculable deceleration from the Sun's dwindling gravity. Yet the data told a different story. An unknown force was acting upon the pioneers, producing a tiny, continuous, and utterly unexpected deceleration. This wasn't a sudden jolt, it was a minuscule, constant push back toward the Sun, a gentle cosmic break so small it was equivalent to the gravitational pull you would feel from a single grain of sand held in your hand. But in the exquisitely precise world of orbital mechanics, even a discrepancy this small, if left unexplained, could point to a monumental flaw in our understanding of the universe. For over 2 decades, this tiny anomaly haunted the corridors of theoretical physics. Dubbed the Pioneer Anomaly, it became one of the most tantalizing puzzles in modern science. Was it evidence of some exotic form of dark matter tugging at the spacecraft? Could it be a sign that Einstein's theory of general relativity needed a slight modification at the vast scales of the solar system? The most thrilling hypothesis suggested we were seeing the first hints of new physics, a crack in the foundational models of reality that could unlock secrets about gravity itself. The scientific community was abuzz with theories, each one more profound than the last, as this persistent whisper from 2 aging probes threatened to rewrite the textbooks. The answer, when it finally came, was not found in the distant realms of theoretical physics, but in the mundane, practical reality of the spacecraft themselves. A small, dedicated team of researchers embarked on a monumental digital archaeology project, recovering decades-old design documents, telemetry data, and even original computer code from obsolete formats. They built a painstakingly detailed computer model of the Pioneer spacecraft, accounting for every possible nook and cranny, and that's when they found the culprit. The Pioneers generated heat from their radioactive power sources, and that heat had to radiate away into space. As it streamed out from the craft's electrical systems and warmed the multi-layered insulation blankets, the photons of this thermal radiation carried away a tiny amount of momentum. Most of this radiation was symmetrical, but a little more heat was emitted from the back of the spacecraft's dish antennae than from the front. This created a net recoil force, a photon thrust, that acted exactly like a gentle, constant brake, pushing the Pioneers back toward the sun. The shock wasn't in the discovery of new physics, but in the stunning realization of how a simple, overlooked engineering effect, the gentle pressure of escaping heat, could mimic the signature of a fundamental revolution in our understanding of the cosmos for more than 20 years. The resolution of the Pioneer anomaly is a masterclass in scientific humility. It demonstrates that sometimes the most profound mysteries are not solved by looking out toward the edges of the known universe, but by looking inward, by meticulously questioning our own instruments and assumptions. It was a breathtaking reminder that before we can chase the ghosts of dark energy or modified gravity, we must first be certain we are not simply seeing the shadow of our own machinery. Sometimes the universe's greatest secrets aren't hiding in the deep black of space, but in the faint, persistent static of a faulty receiver. While the Pioneers presented a puzzle of motion, another monumental discovery was born from a problem that seemed far more mundane, an annoying, inescapable hiss that two radio astronomers just could not get rid of. At Bell Labs in New Jersey in the mid-1960s, Arno Penzias and Robert Wilson were not trying to revolutionize cosmology. They were simply trying to use a massive, ultra-sensitive horn antenna to study radio waves from our own galaxy. But their work was plagued by a persistent, uniform noise that came from every direction in the sky, a faint microwave static that was present 24 hours a day. It was an engineer's nightmare, an uninvited guest in their data that refused to leave. They embarked on a meticulous and often comical quest to track down the source of this interference. They checked all their electronics, tightened every connection, and examined the entire apparatus for faults. The signal remained. Then they considered a more tangible and far messier possibility. A pair of pigeons had taken up residence inside the giant horn of the antenna. Convinced that the birds and their, droppings might be the source of the mysterious thermal noise, they carefully evicted the pigeons and scrubbed the antenna clean of what Penzias would later diplomatically call a white dielectric material. Yet, after all that effort, the hiss was still there, just as strong and just as baffling as before. They were at their wits' end. They had a state-of-the-art instrument, and it was seemingly broken, picking up a signal that made no sense for their intended observations. It was a noise that, by all accounts, shouldn't exist. Meanwhile, just a short distance away at Princeton University, a team of physicists led by Robert Dicke was building a very different kind of experiment. They were actively searching for a theoretical remnant of the universe's birth. The prevailing Big Bang theory suggested that the entire cosmos began in a state of incredible heat and density. As it expanded and cooled about 380,000 years after the initial moment, the fog of primordial plasma would have cleared, allowing light to travel freely for the first time. This first flash of light, stretched and cooled by the expansion of the universe over billions of years, should now permeate all of space as a faint, cold bath of microwave radiation, a cosmic fossil from the very dawn of time. Dicke and his team were literally building a radio receiver to go look for this afterglow. fate intervened when Penzias, frustrated, happened to call a colleague at MIT who knew about the Princeton group's search. The connection was made and the two teams arranged to meet. The moment of realization was one of the most stunning in scientific history. The Bell Labs engineers described their inexplicable, omnipresent noise. The Princeton theorists immediately understood what they were hearing. That wasn't faulty equipment or pigeon interference. That was the echo of creation itself. The annoying hiss was the cosmic microwave background, the cooled-down remnant of the fireball that began our universe. Penzias and Wilson had accidentally stumbled upon the most important evidence for the Big Bang while trying to fix what they thought was a broken antenna. The impact was immediate and profound. At a stroke, this single, serendipitous discovery completely reshaped the debate about the origin of the cosmos. The steady-state theory, which proposed a universe with no beginning or end, was effectively rendered obsolete. The Big Bang was no longer just an elegant idea. It was a physical reality, its afterglow measurable with a radio telescope. The entire field of cosmology was transformed from a realm of philosophical speculation into a rigorous observational science. Penzias and Wilson had provided a tangible link to the universe's infancy, a baby picture of the cosmos when it was just a fraction of its current age. For this monumental, accidental discovery, they would be awarded the Nobel Prize in Physics in 1978, a testament to the fact that sometimes the most universe-shattering revelations come not from what you're looking for, but from what you can't seem to get rid of. But if the cosmic microwave background was a photograph of the universe's infancy, then the next great shock came from trying to understand its middle age and its ultimate fate. For decades, the biggest question in cosmology was a simple one: how will the universe end? The prevailing wisdom, supported by Einstein's theory of gravity, was that the collective gravitational pull of all the matter in the cosmos was acting like a cosmic brake, steadily slowing down the expansion that began with the Big Bang. The only real debate was about the strength of this brake. Would there be enough matter to eventually halt the expansion and pull everything back together in a fiery, big crunch? Or would the universe just keep expanding forever, cooling down into a dark, frozen, and lonely end? To answer this, two rival teams of astronomers in the late 1990s embarked on an ambitious project, using the universe's own mile markers to measure the slowing of its expansion over billions of years. These mile markers were a specific kind of stellar explosion known as a Type 1 supernova. Think of them as standard candles. A Type 1 supernova occurs in a binary star system when a dense white dwarf star siphons off too much material from its companion, crossing a very precise mass threshold and triggering a thermonuclear explosion. Because this threshold is always the same, the explosions are always almost identical in their intrinsic brightness. This means that if you spot one of these supernovae in a distant galaxy, you can tell how far away it is by how dim it appears. A dimmer supernova is farther away, but you can also measure its redshift, how much its light has been stretched to longer, redder wavelengths by the expansion of the universe. By comparing the distance of these supernovae to their redshift, these teams, the Supernova Cosmology Project and the High Z Supernova Search Team, were effectively building a historical record of how fast the universe was expanding at different points in its past. They were looking for evidence that the expansion was decelerating. What they found, however, was the exact opposite. After painstakingly collecting data from dozens of the most distant supernova ever observed, both teams independently arrived at the same jaw-dropping conclusion. The distant, ancient supernova were fainter than they should have been. This meant they were farther away than anyone had predicted. The data pointed to one inescapable and frankly unbelievable reality. The expansion of the universe was not slowing down at all. It was speeding up. Something was actively working against gravity, pushing galaxies apart from one another at an ever-increasing rate. The initial reaction within the teams was profound disbelief. They spent months and years double-checking, triple-checking, and searching for any possible error. Could it be interstellar dust dimming the light? They ruled it out. Could it be some unknown evolution in the supernova themselves over cosmic time? The evidence didn't support it. The result held firm, and when the two teams announced their findings almost simultaneously in 1998, the entire field of cosmology went into a state of shock. This was not a small adjustment to a model. It was a fundamental overturning of a core assumption about how the cosmos works. It was as if you threw a ball into the air, expecting it to slow down and fall back to Earth, but instead you watched it shoot away from you faster and faster into the sky, defying gravity itself. The implication was staggering. There had to be some form of energy permeating the very fabric of space, a repulsive force that counteracts gravity on the largest scales. This mysterious something was given a name that perfectly captures our ignorance: dark energy. The discovery was so profound that it earned the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. But the award came with a humbling caveat. We still have no idea what dark energy actually is. The best measurements we have today, from missions like the Planck satellite, tell us that dark energy makes up about 68% of the entire universe. The matter we understand, the atoms that make up stars, planets, and us, accounts for less than 5%. The rest is another mystery: dark matter. So, the stunning reality is that the vast majority of the cosmos is composed of two substances we cannot see and do not comprehend. The leading hypothesis is that dark energy is an intrinsic property of empty space itself, a concept Einstein once proposed and then discarded as his greatest blunder. But the calculated strength of this energy is wildly, inexplicably different from what our theories of particle physics predict. This discrepancy is one of the most significant unsolved problems in all of science. The discovery of the accelerating universe was a moment of ultimate scientific triumph that simultaneously revealed just how little we truly understand about the fundamental forces shaping our cosmic destiny. From the vast, accelerating canvas of the entire universe, we now turn our gaze to a single, rusty world next door, a planet whose story has been rewritten not once, but repeatedly by the most shocking of all discoveries: the presence of water. For centuries, through even the most powerful telescopes, Mars presented itself as a dry, desolate wasteland. Its surface was a seemingly lifeless landscape of craters, canyons, and dust, a planet that had clearly died geologically long ago. The narrative was simple and stark. Mars was a cautionary tale of a world that had lost its atmosphere and its water, a frozen desert where the only thing flowing was sand. This was the Mars we thought we knew, a planet of stark beauty but little promise for anything beyond robotic exploration. The first major cracks in this arid narrative appeared not from a rover on the ground but from an eye in the sky. In the early 1970s, NASA Mariner 9 orbiter became the first spacecraft to map the entire Martian surface, and its images sent a jolt through the planetary science community. The photographs revealed features that were hauntingly, unmistakably familiar. There were vast, sinuous channels carved across the landscape, some thousands of miles long and hundreds of miles wide. They snaked across the rusty plains, branching into intricate networks of tributaries that looked exactly like dry riverbeds on Earth. Alongside these were deep, colossal canyons like Valles Marineris, a gash in the planet's crust so vast it could swallow the Grand Canyon whole. The evidence was purely geological, but the implication was staggering. Mars had not always been a desert. In its distant past, it must have had a much thicker atmosphere and a climate warm enough for liquid water to flow freely and powerfully across its surface, carving these immense features over millions of years. The dry, dead planet had once been wet and alive. This revelation shifted the entire focus of Mars exploration. The question was no longer just about geology, it was now about habitability. If water flowed, could life have once gained a foothold? This quest drove the missions of the NASA rovers, beginning with Spirit and Opportunity in 2004. Their mission was to follow the water, and Opportunity delivered a shock that moved the mystery from the geological to the chemical. As it explored the Meridiani Planum, its instruments analyzed the bedrock and made a groundbreaking discovery. It was composed of sulfate-rich sandstone. This specific type of rock on Earth forms in the presence of standing, acidic, and salty water. The rover had not just found evidence of a fleeting stream, it had found proof of an ancient, persistent environment, a shallow, salty sea. This wasn't just a place where water had once rushed, it was a place where water had lingered, a potential habitat for microbial life. The discovery was so definitive that project scientists announced that the area Opportunity was exploring had once been soaking wet. Yet the greatest shocks were still to come, as orbiters like NASA Mars Reconnaissance Orbiter began to study the planet with even more powerful cameras and spectrometers. They started to see something that defied the ancient water narrative entirely, features that appeared to be changing in the present day. On steep, sun-facing crater walls, scientists observed dark, narrow streaks that would appear during the warmer Martian months, lengthen down the slopes, and then fade away when temperatures dropped. They named these features recurring slope lineae, or RSL. The patterns were so consistent with the flow of a liquid that the initial hypothesis was breathtaking. These looked like seeps of liquid water, perhaps incredibly salty brine that could remain liquid in the thin, cold Martian air, trickling down hillsides in our own time. The idea that modern Mars might not be bone dry, that it could still have active, liquid water on or near its surface, even if just in tiny, seeping amounts, was a monumental paradigm shift. It suggested that the planet might still be geochemically active in ways we never imagined, opening up the tantalizing possibility of present-day niches where life could potentially exist. But the Martian water mystery had one more, even more profound, shock in store. While surface water is a thrilling idea, the subsurface has always held even greater promise as a potential refuge for life, shielded from the harsh radiation that bombards the surface. The quest to find a substantial reservoir of liquid water led scientists to point a radar instrument aboard the European Space Agency's Mars Express orbiter at the planet's south pole. The method they used is called radar sounding. They sent radio waves down through the ice and rock, timing how long it took for the signals to bounce back. In 2018, after years of data collection over a specific region, the team announced a discovery that felt like something from science fiction. Beneath 1.5 miles of solid ice, the radar had detected an area that reflected signals brilliantly, an interface that was far brighter than the surrounding rock. The signature was a perfect match for what we see when radar surveys subglacial lakes on Earth, like Lake Vostok buried under the Antarctic ice. They had found a massive, stable body of liquid water, a subsurface lake roughly 12 miles across, buried deep beneath the Martian ice cap. The implications of this buried lake are almost beyond comprehension. This isn't a fleeting seep or an ancient puddle. This is a persistent, large body of liquid water that has likely been stable for millions of years. On Earth, such subglacial lakes are isolated, unique ecosystems, teeming with microbial life that has evolved independently for eons. The confirmed existence of a similar environment on Mars presents the most compelling and direct target in the entire solar system in the search for extraterrestrial life. It is a protected, potentially energy-rich habitat where life that may have originated in Mars's wet past could have retreated and survived to the present day. Each of these discoveries, the ancient river valleys, the salty sea bedrock, the modern-day seeps, and finally the buried lake, has delivered its own unique shock, systematically dismantling the old view of Mars. We now see it not as a dead world, but as a dynamic one with a complex water history, a planet that may still hide its most profound secrets, and perhaps even its inhabitants deep within its watery depths. Just when we thought we had our own cosmic neighborhood figured out, the universe delivered a visitor from a place so far away it defied comprehension, an object that sailed right through our front yard and left every astronomer who saw it utterly bewildered. In October of 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at incredible speed. Initial calculations of its trajectory sent a jolt through the entire astronomy community. This was not a typical asteroid or comet from our own solar system. Its path was hyperbolic, meaning it was not orbiting our sun. It was just passing through, a lone traveler on a journey between stars. It was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first, and it was the first confirmed interstellar object ever detected. The initial shock of its origin was quickly eclipsed by the bizarre characteristics it revealed as telescopes around the world swiveled to observe it. The first major puzzle was its shape. As Oumuamua tumbled through space, its brightness varied dramatically by a factor of 10 in a regular, repeating pattern. This extreme fluctuation in brightness could only mean one thing: the object was not roughly spherical like most asteroids or comets. To account for the data, it had to be highly elongated, shaped like a pancake or perhaps a cigar, with its length estimated to be up to 10 times greater than its width. This was unlike any natural object we had ever seen in our own solar system, a form so strange it seemed to defy the typical processes of cosmic formation. Then came the second and even more puzzling anomaly. As scientists meticulously tracked its path, they realized it was not following a trajectory dictated by the sun's gravity alone. There was an extra push, a tiny but significant non-gravitational acceleration that was altering its course. For a normal comet, this is easily explained. As a comet approaches the sun and heats up, it vents gas and dust from its surface, creating a visible coma and tail that act like a natural rocket engine, nudging it along. The team pointed every instrument they could at Oumuamua, searching for this telltale signature of outgassing. They found nothing: no gas, no dust, no surrounding cloud of material, no tail whatsoever. It was completely dark and inert, a silent, rocky-looking object that was somehow accelerating without any visible means of propulsion. It was as if a car was speeding up without any engine noise or exhaust fumes. This combination of the object's interstellar origin, its bizarre shape, and its mysterious acceleration sent a ripple of excitement and speculation through the scientific world. How could an object accelerate without outgassing? The mainstream scientific community proposed a number of natural explanations. Perhaps it was a fractal-like aggregate of dust, a so-called dust bunny from deep space, so porous and light that radiation pressure from the sun itself could be pushing it along. Or maybe it was a shard of a Pluto-like world from another star system, a chunk of solid nitrogen that was slowly sublimating, producing an invisible gas jet that the telescope simply couldn't detect. Each theory, however, had its own weaknesses. A nitrogen iceberg would have to be exceptionally bright, and Oumuamua was not. A porous dust cloud should have broken apart. No single natural explanation fit all the data perfectly. It was this very gap in our understanding that led Harvard astronomer Avi Loeb to propose his now famous and deeply controversial hypothesis. He suggested that Oumuamua's unusual acceleration and its extreme shape could be explained if it was not a natural object at all, but a piece of advanced alien technology, a light sail. A light sail is a theoretical form of spacecraft propulsion that uses the gentle but constant pressure of sunlight, or starlight, to push a large, thin, reflective sheet through space, exactly the kind of technology a civilization might use for interstellar travel. Loeb argued that a thin, pancake-shaped object of the right size and reflectivity would exhibit the precise kind of non-gravitational acceleration we observed from Oumuamua without needing to vent any gas or dust. It would simply be a giant, discarded sail tumbling through the void after its mission was complete. The reaction to this idea was a profound shockwave in itself, not so much for its content, but for the intense public debate it ignited about the very nature of scientific inquiry. Many in the astronomy community criticized the hypothesis as sensationalistic, arguing that extraordinary claims require extraordinary evidence, and that we should exhaust all possible natural explanations before invoking aliens. The discussion spilled out of academic journals and into the global media, captivating the public imagination in a way few scientific discoveries ever do. At its core, the Oumuamua event forced scientists and the public alike to confront a thrilling and humbling possibility. For the first time in history, we may have been presented with tangible evidence that we are not the only builders in the cosmos, a piece of debris from a civilization far older and more advanced than our own. The true shock of Oumuamua was not just its strange properties, but the profound question it left hanging in the air, a question that remains unanswered. Were we simply visited by a curious piece of natural space rock, or did we, for a fleeting moment, witness the discarded archaeology of a distant star-faring race? While the hunt for interstellar visitors captivated our imaginations, a different kind of mystery was brewing back in our own galactic neighborhood, one that played out not in motion, but in the subtle, rhythmic language of light. Our story now shifts to the Kepler Space Telescope, a remarkable observatory whose primary mission was to stare unblinkingly at a single patch of sky, monitoring the brightness of over 150,000 stars in search of a telltale sign, the gentle, periodic dip in light caused by a planet passing in front of its host star. Kepler was a cosmic statistician, and it excelled at finding patterns. Most of the signals it detected were beautifully regular, predictable little winks that repeated like clockwork every few days, months, or years. It was in this sea of orderly, predictable data that a group of citizen scientists, part of the Planet Hunters project, spotted something that made absolutely no sense at all. The star, catalogued as KIC 8462852, but soon to be known around the world as Tabby's star after the lead scientist on the paper, Tabby, displayed a light curve that was pure chaos. While a transiting planet typically causes a dip of less than 1% in a star's brightness, Tabby's star was experiencing colossal drops, not just one but many, scattered across the years of Kepler data. These weren't the neat, symmetrical dips of a planet. They were irregular, jagged, and staggeringly deep. The most famous of these events, dubbed D800, saw the star's light plummet by a breathtaking 22%. To put that in perspective, if a Jupiter-sized planet, the largest in our solar system, were to pass in front of a sun-like star, it would block only about 1% of the light. For a star to dim by 22%, you would need an object or a collection of objects with a surface area thousands of times larger than Jupiter blotting out the star. This was not the signature of a simple planet. This was the shadow of something vast, complex, and utterly confounding. The initial reaction from the astronomy community was a mix of profound shock and intense skepticism. The first assumption was that the data was faulty, a glitch in Kepler's sensitive electronics, but the signal was real. The next step was to explore every conceivable natural explanation. Could it be a swarm of comets, thousands of them, shattered by a close encounter with another star and now passing in front of Tabby's star in a dense, chaotic cloud? This was the initial hypothesis put forward by Boyajian and her team, but it stretched the limits of plausibility. The amount of cometary material required to create such deep, irregular dimming was orders of magnitude greater than anything we see in our own solar system's Oort cloud. Others proposed that the star itself was young and still surrounded by a massive, clumpy protoplanetary disk of dust and gas, but observations revealed Tabby's star to be a mature, main-sequence star, not a youthful one prone to such violent growing pain. Every conventional model came up short, failing to fully account for the sheer depth and bizarre shape of the dimming events. It was this glaring gap in our understanding that opened the door to one of the most thrilling and controversial ideas in modern astronomy. Jason Wright, an astronomer at Penn State University, and his colleagues famously suggested that the bizarre light pattern could be consistent with a vast alien megastructure. Specifically, they proposed the concept of a Dyson swarm, a colossal collection of energy-harvesting satellites or habitats orbiting a star, built by a Type II civilization on the Kardashev scale to capture a significant fraction of its power output. The irregular, non-periodic dimming could be explained by massive, partially completed structures of different shapes and sizes passing in front of the star, their transits creating the jagged, asymmetric dips in the light curve. The idea was sensational, and it ignited a media firestorm. Suddenly, a technical astronomical puzzle became a global conversation. Were we, for the first time, looking at evidence of an advanced civilization so powerful it could build on a stellar scale? This hypothesis prompted an unprecedented scientific response. The Search for Extraterrestrial Intelligence, or SETI, Institute quickly trained its powerful Allen telescope array on Tabby's star, listening intently for any radio signals that might betray the presence of a technological society. They heard nothing. Further observations across different wavelengths of light began to provide crucial clues. When an object transits a star, the way it dims the light can reveal its composition. A solid object, like a planet or a hypothetical solid megastructure, would block all wavelengths of light equally. However, when scientists observed Tabby's star with the Spitzer Space Telescope in the infrared, they found that the dimming was much less pronounced than it was in visible light. This was the critical piece of the puzzle. Dust behaves in exactly this way. It is more effective at blocking shorter, bluer wavelengths of visible light than longer, redder infrared wavelengths. The data strongly indicated that whatever was blocking the light wasn't a solid, opaque structure, but a vast, fine cloud of microscopic dust particles. Subsequent, intensive monitoring campaigns led by Tabetha Boyajian using the Los Cumbres Observatory Global Telescope Network captured the star in the act of dimming multiple times. They were able to dissect the light in exquisite detail, confirming that the dimming was always chromatic. The color of the light changed during the dips. This was the final nail in the coffin for the solid megastructure hypothesis. The culprit was almost certainly dust, but the mystery of Tabby's star is far from completely solved. We are still left with the fundamental, shocking question: what is producing such immense, irregular clouds of dust? The leading theory now suggests a planet or a group of planets with extraordinarily active volcanic or geological systems, periodically erupting and spewing colossal amounts of dust into space. Another idea posits the recent collision of two or more planetary bodies, creating a massive debris field that is now intermittently passing in front of the star. The true shock of Tabby's star wasn't that it was aliens, but that it revealed a natural astrophysical phenomenon so extreme and so bizarre that, for a time, the only conceivable explanation seemed to be intelligence. It stands as a powerful lesson in cosmic humility, a blazing reminder that the universe is a factory of wonders, capable of producing mysteries that push the very boundaries of our imagination. And yet, for all the mystery surrounding interstellar visitors and strangely dimming stars, perhaps no single moment in 21st century astronomy quite captured the public's imagination and the scientific community's awe like the day we finally saw the unseeable. For generations, black holes existed as the ultimate cosmic paradox, objects of immense theoretical power that were, by their very nature, impossible to observe directly. They were the terrifying and beautiful prediction of Einstein's general relativity, regions of space where gravity is so intense that nothing, not even light, can escape their grasp. We knew they were there, of course. We could see their gravitational influence like watching dancers waltz around an empty ballroom floor, inferring the presence of their massive, invisible partner from the stellar motions they induced. We had listened to the ripples in space-time when two of them collided, but to actually see one, to lay eyes on the literal edge of reality, that was a dream that seemed forever beyond our reach. The fundamental problem is one of staggering scale and technological limitation. To even hope to see the shadow of a black hole, you need a telescope with a resolution so sharp it could read a newspaper in New York City from a sidewalk cafe in Paris. No single telescope on Earth, not even the mighty Hubble Space Telescope, possesses that kind of power. The solution was as brilliant as it was audacious. Instead of building one impossibly large dish, scientists would create a virtual telescope the size of our entire planet. This was the genesis of the Event Horizon Telescope, or EIT, a global collaboration linking 8 radio observatories from the high, dry deserts of Atacama to the frigid peaks of the South Pole. By using a technique called very long baseline interferometry and synchronizing each observatory's data with exquisitely precise atomic clocks, these scattered dishes could act as one single Earth-sized lens, peering into the heart of darkness itself. The target was a supermassive black hole 55 million light-years away, residing at the core of the galaxy Messier 87. This cosmic behemoth contains the mass of 6.5 billion suns, crushed into a region of space not much larger than our entire solar system. For over a decade, the EHT team prepared, developing custom-built hardware and complex algorithms to process the mind-boggling amount of data they would collect. In April of 2017, the weather cooperated across all 8 sites, offering a rare global window of clear skies. For 5 tense nights, the telescopes stared in unison at M87, gathering over 5 petabytes of raw data. So much information that it was actually cheaper and faster to ship physical hard drives filled with the data on airplanes to centralized processing facilities than to try to send it over the internet. Then began the 2-year global effort to develop the algorithms and painstakingly calibrate the data to produce a coherent image from this scattered, global harvest of radio waves. The challenge was monumental, akin to trying to piece together a symphony from a few random notes heard on different continents. The tension within the collaboration was palpable. Had it worked, had they actually captured the shadow, the moment of truth arrived in the summer of 2018. The data was processed using multiple independent teams to avoid bias, and the results were then combined. The day the final image was revealed to the entire team, the room fell into a stunned silence, followed by an eruption of emotion. There it was, a perfect fiery ring of light, asymmetrically bright, encircling a central region of profound darkness, the black hole's shadow. It was a sight that was instantly, hauntingly familiar, matching the predictions of general relativity with an almost unbelievable accuracy. The dark central void wasn't the black hole itself, but its shadow. The event horizon's gravitational lensing effect, warping and capturing the light from the hot, swirling accretion disk behind it. The public announcement on April 10, 2019, was a landmark event in science communication. The image, this luminous orange donut against a black background, instantly circled the globe, appearing on front pages and news broadcasts everywhere. For scientists, the shock was multi-layered. Yes, it was a triumphant confirmation of Einstein's theory, which had once again passed a test in the most extreme regime imaginable. But more than that, it was a visceral, aesthetic shock. For the first time, humanity was staring directly at the ultimate symbol of cosmic power and mystery, a place where the laws of physics as we know them break down. Theorists were stunned by how clean and perfect the data was, and how beautifully it aligned with decades of complex simulations. It was a moment that transformed a mathematical abstraction into a tangible, almost touchable cosmic object. It was no longer just an idea, it was a place. That single image did more than just prove black holes exist. It gave humanity a shared icon for the infinite wonder and profound mystery of the cosmos, a shocking and beautiful window into the heart of darkness. Just when we thought Mars had revealed its final secret about water, the red planet delivered another curveball, one that didn't involve vast oceans or buried lakes, but a whiff of a gas that, on our own planet, is the signature of life itself. This is the mystery of Martian methane, a puzzle that has left planetary scientists utterly divided and has turned a humble rover trundling across an ancient lakebed into the center of one of the most heated debates in modern science. The story begins not with a single, definitive discovery, but with a series of tantalizing and at times contradictory whispers from the thin Martian air. For decades, telescopes from Earth and orbiting spacecraft had offered hints, fleeting detections of methane that were often dismissed as potential errors or the result of contamination from Earth itself. The scientific community was rightly skeptical. Detecting trace amounts of a specific gas from millions of miles away is an immense technical challenge. This all changed with the arrival of NAS, a Curiosity rover in Gale Crater in 2012. This car-sized laboratory was built for this kind of investigation, equipped with a sophisticated onboard chemistry lab called the Sample Analysis at Mars, or SAM. Unlike orbiters, SAM could sniff the air directly, ingesting tiny samples of the Martian atmosphere and analyzing their composition with incredible precision. The initial results, published in 2014, sent a jolt through the world of planetary science. Curiosity had confirmed it. There was methane on Mars, albeit in a tiny background concentration of around 0.7 parts per billion. To put that in perspective, the methane in Earth's atmosphere, much of it from biological sources like livestock and wetlands, is about 1,800 parts per billion. The Martian signal was vanishingly small, but its mere presence was a monumental shock. The real stunner, however, wasn't the background level, it was what happened next. Periodically, and without any clear warning, Curiosity's instruments would register sudden, dramatic spikes in methane concentration. In late 2013 and again in 2019, the rover measured levels that skyrocketed, soaring to around 21 parts per billion, a tenfold increase that appeared abruptly and then vanished back to background levels within a matter of weeks. These events were not gradual, they were sharp, localized puffs of gas, as if the rover had driven directly through an invisible, dissipating plume. This behavior was the core of the mystery. Methane is not a stable molecule in the Martian atmosphere. Solar radiation and chemical reactions should break it down in just a few hundred years. To see these fresh, modern-day spikes means the gas is being actively released now from a source or sources very close to where Curiosity was roving. The universe, it seemed, was presenting us with a classic whodunit played out on an alien world. The shock of this discovery immediately fractured the scientific community into two passionate camps, each championing a fundamentally different explanation for the gas's origin. The first and perhaps most thrilling possibility is biology. On Earth, the vast majority of atmospheric methane is produced by living organisms, microbes known as methanogens, which thrive in places devoid of oxygen like the guts of animals or deep underwater sediments, consume simple chemicals and exhale methane as a waste product. The tantalizing, almost science-fictional prospect is that similar, subterranean microbes could be living deep beneath the cold, dry surface of Mars, protected from radiation, perhaps in the very same briny aquifers or subglacial lakes we've detected. In this scenario, these Martian microbes would be a form of relic life, a biosphere that has hung on for billions of years in isolated pockets, occasionally burping pockets of methane that seep to the surface and into the atmosphere. The mere possibility that a robot on Mars might be sniffing the metabolic exhaust of alien life is a concept so profound it redefines our place in the cosmos. The second, more conservative but equally fascinating explanation is geology. Mars is a geologically active world in its own right, and there are well-understood non-biological processes known as serpentinization that can produce methane. This occurs when certain types of iron-rich rocks, like olivine, come into contact with water in a chemical reaction that generates methane as a byproduct. We see this happen deep within the Earth's crust and at hydrothermal vents on the ocean floor. On Mars, this process could be ongoing, with residual heat from the planet's interior driving these reactions in aquifers deep below the surface. Furthermore, methane could also be trapped in ancient, ice-like structures called clathrates, stored underground for eons and only occasionally released when the overlying rock is fractured by masquaks or shifts in temperature. The geological hypothesis suggests that Mars is simply breathing, releasing gases from its ancient rocky interior through entirely natural abiotic means. The debate between these two possibilities is fierce because the data so far has been maddeningly ambiguous. The same gas that on Earth screams life can, under the right conditions, be produced by completely sterile processes. The shock for scientists isn't just the detection of the methane. It's the frustrating inability to distinguish its source with the tools we currently have on the planet. Curiosity can tell us the gas is there and in what quantity, but its instruments cannot determine whether the carbon in the methane molecules comes from a biological factory or a geological one. This fundamental limitation has turned every new day to point into a Rorschach test where researchers see the evidence that confirms their own biases. The plot thickened even further with the arrival of the European Russian Trace Gas Orbiter, or TJO, in 2016. This sophisticated satellite was specifically designed to solve the methane mystery from orbit, using incredibly sensitive spectrometers to map the gas across the entire planet. The shocking part, in its first several years of operation, the TJO found almost nothing. It detected no significant background methane and certainly none of the large plumes that Curiosity had reported from the surface. This was a direct contradiction that left everyone stunned. How could the rover on the ground be driving through dense methane clouds while the orbiter high above saw only a pristine, methane-free atmosphere? This discrepancy has forced scientists back to the drawing board, leading to a new wave of fascinating theories. One compelling idea is a destructive cycle at the surface. The hypothesis suggests that methane is indeed being released from the ground, perhaps at night when the atmosphere is calm. But before it can rise and mix into the broader atmosphere where the TJO can detect it, the weak Martian dawn sun hits the soil, triggering chemical reactions that create potent oxidants like perchlorates. These compounds could act like a planetary-scale cleaning agent, rapidly breaking down the methane right at the surface within mere hours of its release. In this scenario, Curiosity is like a person standing in a forest just as a single tree falls. It detects the local event, while the TJO in orbit is listening for the sound of the entire forest falling and hears nothing. Another theory suggests the releases are so localized and brief that the TJO simply hasn't been looking at the right place at the right time. The methane on Mars mystery remains one of the most tantalizing and unresolved shocks in planetary science. It is a detective story with multiple suspects, conflicting eyewitness accounts, and a missing murder weapon. It pits a ground-level snapshot against a global overview and biology against geology. Every new spike detected by Curiosity sends a fresh wave of excitement and frantic analysis through the team, a moment where they must ask themselves if they are seeing the signature of a non-living planet or the first, faint breath of a second genesis of life in our solar system. This ongoing puzzle exemplifies the very essence of exploration, where a single, simple molecule, just one carbon atom bonded to 4 hydrogen atoms, has the power to hold the entire scientific world in suspense, waiting for the next clue that might finally tell us if we are alone. But for all the mysteries we find on planets and stars within our view, some of the most profound shocks come from what we cannot see at all, a ghostly hand tugging at our entire galaxy from the depths of intergalactic space. This story begins not with a new discovery, but with the careful, meticulous mapping of the cosmos that started in the latter half of the 20th century. For a long time, we understood the universe's expansion as a simple, uniform flow, with all galaxies receding from each other as space itself stretches. Yet, as astronomers began to plot the precise velocities of thousands of galaxies, they noticed something deeply unsettling. Our own Milky Way, along with our entire local group of galaxies, was not moving with the serene flow of the cosmic expansion. We were careening through space at a staggering speed of over 1 million miles per hour in a specific direction, deviating massively from the overall Hubble flow. It was as if you were floating down a wide, calm river, only to realize your boat was being powerfully pulled toward a hidden waterfall just beyond the horizon. The universe, it seemed, had a current, and we were caught in its grip. The source of this colossal pull was a mystery so vast it defied easy explanation. Dubbed the Great Attractor, this phenomenon wasn't a single object, but a concentration of mass so immense that its gravitational influence was dominating an entire region of space, a cosmic watershed spanning hundreds of millions of light years. The initial shock for scientists was twofold. First was the sheer scale of the motion itself, a velocity that hinted at a mass equivalent to tens of thousands of Milky Way galaxies all clustered together. Second, and more frustratingly, was the location. When astronomers pointed their telescopes toward the center of this gravitational pull, in the direction of the southern constellations Centaurus and Norma, they found their view almost completely blocked. The heart of the Great Attractor lies directly behind the plane of our own Milky Way galaxy, a region so choked with cosmic gas and dust that it's known to astronomers as the zone of avoidance. It was the ultimate cosmic irony. The very thing pulling us was hidden behind the crowded stellar city we call home. We were like detectives trying to identify a master criminal who was standing directly behind a brightly lit, bustling crowd, completely obscured from view. This led to a decades-long scientific treasure hunt, using instruments that could peer through the obscuring dust not with visible light, but with radio waves and X-rays. Slowly, a clearer picture began to emerge, and with it, an even greater shock. The Great Attractor was not the final destination. Instead, it appeared to be just a waypoint, a local mass concentration that was itself part of something infinitely larger and more terrifying. Our entire galactic neighborhood, including the Great Attractor, is being pulled toward an even more massive structure known as the Shapley supercluster, a staggering collection of over 8,000 galaxies located over 650 million light-years away. The gravitational hierarchy was becoming clear. Our local group is falling toward the Great Attractor, and the Great Attractor, in turn, is falling toward Shapley. It was a cosmic unveiling of an entire hidden geography, a map of flowing galaxies that revealed the large-scale structure of the universe in a way no one had fully appreciated before. The profound implication of this discovery is that the serene, uniform expansion of the universe is only the backdrop. Superimposed upon it are these violent, local rivers of motion, where vast streams of galaxies flow along filaments of dark matter toward the densest nodes in the cosmic web. The Great Attractor was our first, shocking glimpse into this dynamic and lumpy cosmos. It forced astronomers to abandon the idea of a perfectly smooth universe and accept one that is clumpy and structured on the grandest scales, with gravity acting as the great sculptor over billions of years. The mystery is not entirely solved. The exact mass of the Great Attractor and its role within the even larger Laniakea supercluster, of which it forms the core, are still active areas of research. But the initial shock of its discovery permanently altered our cosmic perspective. We are not merely observers of an expanding universe. We are participants in a grand, gravitational dance, riding a galaxy that is being pulled relentlessly toward an unseen and immense concentration of mass, a hidden heart of darkness whose full nature we are still striving to understand. While the Great Attractor revealed a slow, cosmic tug-of-war, our next shock arrives not as a gentle pull, but as a deafening millionth of a second shriek from the void. It began in 2007 when astronomer Duncan Lorimer and his student David Narkevic were sifting through archived data from the Parkes Radio Telescope in Australia, recorded 6 years earlier. They were looking for new pulsars, the steady, ticking lighthouses of the galaxy. But buried in that old data was something that defied all categorization, a single, colossal burst of radio energy that leaped off the chart. It was unimaginably brief, lasting just 5 milliseconds faster than the blink of an eye. But in that fleeting instant, it released as much energy as the sun gives off over 80 days. The signal was so bright and so dispersed, it clearly indicated a journey of billions of light years. They had stumbled upon the first known fast radio burst, or FRB, a cosmic event so powerful and so brief it left astronomers utterly stunned and completely baffled. The initial discovery sent a shockwave of skepticism through the community. A single, unrepeatable event of such immense power but no visible afterglow in any other wavelength. The immediate suspicion was that it had to be some form of local interference, a glitch from a passing microwave oven in the observatory's kitchen or an errant satellite signal. For years, the Lorimer burst remained a tantalizing but unconfirmed anomaly, a potential ghost in the machine that many were hesitant to accept as real. But then, other telescopes started finding them. The Arecibo dish in Puerto Rico, the Green Bank telescope in West Virginia, and others began detecting these brilliant millisecond flashes. Each new detection confirmed that FRBs were not only real but also happening all over the sky, several times a day across the entire universe. The shock was no longer about their existence but about their origin. What natural phenomenon could possibly be so brief, so energetic, and so common? Just as the scientific community was getting used to the idea of these mysterious one-off explosions, the universe delivered its second, even more profound shock. In 2016, after painstakingly monitoring a source known as FRB 121102, the Arecibo telescope witnessed the impossible, the burst repeated. It wasn't a cataclysmic, self-destructing event like a supernova or a neutron star collision. This was something that could happen again and again, a repeater. This single observation immediately overturned the leading theories and split FRBs into two distinct families, the one-off, seemingly singular events and the rare but crucial repeaters. The discovery of repeating FRBs was the key that unlocked the mystery, because it meant astronomers could now point the world's most powerful telescopes at a known location and wait for it to fire again, allowing them to triangulate its home galaxy and study its environment in exquisite detail. This is precisely what happened with the most famous repeater, FRB 180916. Through a coordinated global effort using 8 telescopes spanning from Japan to Europe to North America, scientists pinpointed its origin to a spiral galaxy 500 million light-years away. They were even able to localize it to a specific region within that galaxy, a region of active star formation. This crucial piece of evidence strongly pointed toward a young, magnetically hypercharged neutron star known as a magnetar as the most likely culprit. Magnetars possess magnetic fields 1,000 trillion times stronger than Earth's, and the theoretical energy released in a starquake on their crust could potentially explain the immense power of an FRB. The leading hypothesis is that these cosmic tremors crack the star's rigid surface, unleashing a firestorm of particles and energy that we see as a brilliant radio flash. Yet the universe loves complexity. Not all FRBs fit this neat picture. Some one-off bursts are far more energetic than any repeater, suggesting there might be multiple pathways to creating these signals. Some theorists propose collisions between incredibly dense objects, like a neutron star and an asteroid or even 2 neutron stars. Others have explored the possibility of blitzars, a hypothetical phenomenon where a supermassive neutron star, too heavy to be stable, collapses almost instantly into a black hole, shedding its magnetic field in one final catastrophic radio scream. And of course, the sheer power and brevity of these signals inevitably led to a speculative, thrilling, and controversial idea. Could some FRBs be artificial? Could they be the byproduct of unimaginably advanced technology, perhaps interstellar light sails being pushed by powerful radio beams, or even bursts of communication from a distant civilization? While the natural magnetar explanation currently holds the most weight, the mere fact that such exotic possibilities are seriously discussed in scientific papers highlights just how shocking and transformative these fleeting radio screams have been. They have opened an entirely new window into the most violent and energetic processes in the cosmos, reminding us that even in the quiet, dark spaces between the stars, the universe is crackling with a fierce and mysterious energy. Yet even as the bizarre dimming of Tabby's star began to find plausible natural explanations, another celestial anomaly would soon emerge from the data, one that took the idea of alien megastructures from fringe speculation to a serious, if fleeting, subject of scientific discourse. This time, the mystery was not found in the data from the Kepler telescope, but from its successor, NAS, a transiting exoplanet survey satellite, or TESS. While TESS was busy surveying the brightest stars near our Sun for new worlds, a team of citizen scientists and professional astronomers were digging through a different treasure trove, decades of photographic plates from the digitized sky survey. They were on the hunt for stars that exhibited extreme changes in brightness over long timescales, and in 2021, they found a candidate so peculiar it seemed to defy all conventional classification. The star, catalogued under the unassuming name TYC 611111621, displayed a light curve that was, in a word, unbelievable. Unlike the chaotic dips of Tabby's star, this star's behavior was starkly different. The historical data showed that, over the course of the 20th century, the star's light had plummeted in a series of steps, dimming by a staggering amount, up to 30%, and then staying at that new, lower level of brightness for decades at a time. Imagine looking up at a familiar star in the night sky and watching it, over a human lifetime, steadily fade until it has lost nearly a third of its brilliance, remaining faint for generations. This was not the brief, jagged flicker of a passing dust cloud. This was a profound, permanent-seeming dimming event that played out on a timescale almost geological in its slowness. The initial reaction among the small team that discovered it was a mix of profound confusion and electrifying excitement. Every natural explanation they tested seemed to fall short. Could it be a vast cloud of interstellar dust drifting between the star and us? Such dust clouds do exist, but they are typically immense, spanning light years, and they don't produce these clean, step-like transitions in brightness. Furthermore, the dimming was what astronomers call gray, meaning it blocked all wavelengths of light equally, which is the signature of large, solid particles, not the fine dust that preferentially blocks blue light. Was it some bizarre, intrinsic property of the star itself? A star entering a final, unstable phase of its life can change brightness dramatically, but such changes are accompanied by massive shifts in its temperature and color. TYC 611111621 remained steadfastly stable in its spectral class even as its light faded away. It was as if a dimmer switch had been turned, not on the star, but somewhere between the star and us. It was this specific combination of characteristics, the immense, gray, step-like dimming over a century, that led the researchers to openly discuss the most extraordinary possibility in their paper. They noted that the light curve was eerily consistent with the theoretical signature of a Dyson sphere under construction. A Dyson sphere, first proposed by physicist Freeman Dyson, is not typically a solid shell, but rather a vast swarm of energy collecting satellites or habitats that would gradually encircle a star, capturing an ever-increasing fraction of its light for use by an advanced civilization. The step-like dimming of TYC 6111111621 could, in theory, be explained by the sequential construction and deployment of these massive orbital structures. Each new, completed segment of the swarm would block another portion of the star's light, causing a sharp drop in brightness that would then remain constant until the next major construction phase began decades later. The idea was so audacious that it sent a tremor of excitement through the entire field of astronomy and the public imagination. Of course, the scientific community responded with a healthy dose of skepticism, immediately embarking on a race to gather more data. Follow-up observations across multiple wavelengths, from the infrared to the ultraviolet, were crucial. A solid, completed Dyson sphere would absorb the star's visible light and re-radiate it as waste heat in the infrared, creating a huge infrared excess. When astronomers looked, they found no such excess. The star's energy budget appeared normal. The missing visible light wasn't being dumped as heat elsewhere in the spectrum. This was a major blow to the solid megastructure hypothesis. Furthermore, more detailed analysis began to point toward a more natural, if still exotic, culprit, a vast, dense disk of debris, possibly the shattered remains of a planet or moon, orbiting the star in a way that created these long-term gray eclipses. The material in this disk would have to be made of unusually large, opaque chunks to account for the gray dimming, but such a cataclysmic collision in the star's system was a far more plausible, if still rare, astrophysical event. The true legacy of the TYC 6111111621 mystery, therefore, is not that it proved the existence of alien engineers, but that it beautifully illustrates a fundamental shift in how we explore the cosmos. For the first time in history, we are swimming in such a vast ocean of astronomical data that we can discover anomalies that are not just unexpected, but that actively challenge the very boundaries of what we consider possible. These bizarre signals force us to move through a structured process of scientific inquiry, first ruling out instrumental error, then exhausting every conceivable natural explanation, and only then, with great caution and humility, allowing ourselves to consider the most extraordinary possibilities. The shock was not the potential discovery of a Dyson sphere, but the realization that our data has become so precise that we can now even frame the question in a scientifically meaningful way. These anomalous stars are like cosmic Rorschach tests, revealing as much about our own hopes and imagination as they do about the universe's endless capacity for wonder. They stand as beacons at the edge of our understanding, reminding us that the line between science fiction and science fact is often nothing more than the next great observation. Yet for all the cosmic mysteries unfolding in distant galaxies, sometimes the greatest shocks are hiding in our own celestial backyard, forcing us to question the most fundamental map we have, the one of our own solar system. For generations, we were taught a simple, elegant model: 8 planets orbiting the Sun, with a belt of asteroids and a distant, icy realm of comets known as the Kuiper Belt. It was a tidy, seemingly complete family portrait, but in the early 21st century, that portrait began to develop some very strange cracks that would eventually point toward the existence of a colossal, unseen world, a ghost in the machine of our own cosmic neighborhood. The shock came not from seeing this world, but from seeing its shadow, the bizarre, inexplicable alignment of tiny, frozen objects in the outer darkness. The story begins not with a single discovery, but with a pattern that emerged from patient, long-term observations of the Kuiper Belt. This region beyond Neptune is populated by thousands of small, icy bodies known as trans-Neptunian objects, or TNOS. Most of these objects have orbits that are randomly oriented, a scattered collection of paths like a swarm of bees. But around 2013, astronomers Chad Trujillo and Scott Shepard noticed something deeply peculiar. A small group of the most distant TNOS, those with orbits taking them incredibly far from the Sun, were not randomly scattered at all. Their elongated orbits were mysteriously clustered, all pointing in roughly the same direction in space and all tilted at a similar angle. Statistically, this was like rolling a handful of marbles onto a floor and watching them all line up in a perfect row. The probability of this happening by pure chance was calculated to be a mere 0.007%. It was a statistical scream in the data, a blatant sign that something was herding these distant objects, organizing their orbits through a powerful, persistent gravitational influence. The initial reaction in the planetary science community was one of profound skepticism, mixed with a growing sense of awe. How could this be? Neptune's gravity was far too weak at these immense distances to orchestrate such a precise alignment. The only plausible explanation, proposed in a landmark 2016 paper by astronomers Konstantin Batygin and Mike Brown, was as shocking as it was simple: a massive yet undiscovered planet. This hypothetical world, which they dubbed Planet 9, would need to be a true giant, a super-Earth with a mass roughly 5 to 10 times that of our own planet. Its orbit would be colossal and highly elliptical, swinging hundreds of times farther from the Sun than Earth, taking perhaps 10,000 to 20,000 years to complete a single, lonely journey around our star. According to their models, the gravitational pull of this distant behemoth over billions of years would have precisely shepherded the orbits of those farthest TNOS into the clustered configuration we observe today. It was a masterful piece of celestial detective work, inferring the existence of a giant from the synchronized dance of the smallest, most distant specks of ice. The implications of this hypothesis send shivers down the spine. If Planet 9 is real, it would fundamentally rewrite the story of our solar system's formation and evolution. Its immense size and vast orbit place it in a category of planet we don't currently have in our own system, an ice giant exile, flung outward during the solar system's chaotic early days by gravitational interactions with Jupiter or Saturn. Its existence would solve other lingering mysteries, too, such as why the average orbital plane of the solar system is tilted by about 6 degrees relative to the Sun's equator. The gentle, persistent tug of a distant, massive Planet 9 could have slowly torqued the entire solar system over billions of years. Furthermore, its gravitational influence might explain the peculiar orbits of a few known objects that seem to be orbiting perpendicular to the rest of the planets, as if they were pushed into their strange paths by a massive perturber. This isn't just about adding one more planet to the list. It's about discovering a central architect that has been secretly shaping the outer reaches of our cosmic home for eons. The hunt for this phantom world is now one of the most thrilling endeavors in modern astronomy, a massive international effort that combines cutting-edge mathematics with the power of some of the world's largest telescopes. The challenge is staggering. Planet 9, if it exists, is incredibly faint and moves incredibly slowly across the sky. Finding it is like searching for a single, dim star in an area of sky the size of thousands of full moons. Astronomers are using complex algorithms to predict its possible location based on the orbits of the TNOS, and then directing powerful instruments like the Subaru telescope in Hawaii and the Victor M. Blanco telescope in Chile to scan those patches of sky night after night, looking for a single, slow-moving point of light that doesn't match any known star or galaxy. It is a painstaking needle-in-a-haystack search, but one fueled by the electrifying possibility of a discovery that would be the astronomical equivalent of finding a new continent on a map we thought was complete. The ongoing nature of this search is in itself a profound shock to our understanding. We have sent probes to every planet, landed rovers on Mars, and flown a spacecraft through the atmosphere of a Saturnian moon. We consider ourselves to be intimate residents of this solar system, and yet the possibility remains that a world larger than Earth has been lurking in the perpetual twilight of the outer solar system, silently governing the motions of distant ice dwarfs completely unknown to us until now. The Planet 9 hypothesis is a breathtaking reminder that exploration is never truly finished, that even in the places we think we know best, the universe can still hide giants in the shadows, waiting for a curious mind to finally piece together the clues and reveal a hidden king of the cosmic frontier. While we search for ghosts in the outer solar system, our next moment of shock comes from a discovery that didn't involve light, radio waves, or any form of electromagnetic radiation at all. Instead, it was felt as a literal tremor in the fabric of reality itself, a vibration so minuscule it required the most precise measuring device ever built to sense it. For a century, one of the most brilliant predictions of Einstein's general theory of relativity had remained just that, a prediction. He theorized that cataclysmic events in the cosmos, like the collision of black holes, would generate ripples in space-time, waves of gravitational energy that would propagate outward at the speed of light, stretching and squeezing everything in their path. But Einstein himself was deeply skeptical that we would ever detect them. The distortions would be impossibly small. The signal from even the most violent event would change the length of a 4-kilometer long instrument by less than 1,000th the diameter of a single proton. It was like trying to measure the distance to the nearest star with an accuracy of the width of a human hair. For decades, physicists tried and failed, and many began to wonder if this cornerstone of modern physics would forever remain beyond our reach. That all changed on the morning of September 14, 2015. At the two facilities of the Laser Interferometer Gravitational Wave Observatory, or LIGO, in Louisiana and Washington State, the newly upgraded detectors were undergoing their final preparations before official data taking began. These are not ordinary telescopes. Each LIGO observatory consists of two 4-kilometer long vacuum tubes arranged in a giant L shape. A laser beam is split and sent down each arm, bouncing off perfectly suspended mirrors to be recombined. In the absence of any disturbance, the light waves cancel each other out through a process called interference, and the detector sees darkness. But when a gravitational wave passes through the Earth, it minutely warps space-time, making one arm of the L temporarily longer and the other shorter. This changes the distance the laser light travels, disrupting the perfect cancellation and allowing a flicker of light to reach the sensor. The entire system is designed to isolate the mirrors from every conceivable earthly vibration, from distant earthquakes to the rumble of logging trucks and even the footsteps of people walking nearby. At 5:51 in the morning Eastern Daylight Time, both detectors, separated by 3,000 kilometers, registered a signal. It wasn't a flicker, it was a roar. The data showed a characteristic pattern that started at a low frequency and then rapidly increased in both pitch and amplitude, a sound that physicists call a chirp. In the control rooms, the initial reaction was not excitement but profound suspicion. The signal, designated GW150914 for the date, was almost too perfect, and it had arrived before the official observation run had even started. The teams immediately assumed it was a blind injection, a secret test where the scientists inject a fake signal into the detectors to keep the data analysis teams on their toes and to test their response procedures. For weeks, researchers desperately searched for any sign of a malfunction or a malicious hack. They found nothing. The signal was clean, it was strong, and it was real. The shock began to set in. They had done it. They had captured the sound of two black holes, one with 36 times the mass of the Sun and the other 29, colliding and merging into a single, more massive black hole some 1.3 billion light-years away. For a fleeting fraction of a second, the energy radiated in gravitational waves was greater than the combined light output of every star in the observable universe. The announcement on February 11, 2016, was a landmark moment in the history of science, a confirmation that sent ripples of its own through the global physics community. The shock was not just that they had detected gravitational waves, but that the very first detection was of an event that was itself a surprise. Before this, there was no definitive proof that binary black hole systems like this even existed, let alone that they could merge. The discovery simultaneously confirmed two monumental pieces of physics: the existence of gravitational waves and the existence of stellar mass binary black holes. It was a direct validation of Einstein's genius a full century after his prediction, but it also immediately opened an entirely new field of astronomy. For all of human history, we have studied the cosmos by observing light, visible, radio, X-ray, gamma-ray. Now we could listen to it. Gravitational wave astronomy allows us to perceive the universe through the vibrations of spacetime itself, to hear the dark, silent events that emit no light whatsoever. The implications of this new sense are staggering. It's like being deaf and suddenly gaining the ability to hear, discovering a whole symphony that was playing all around us that we never knew existed. We are no longer just watching the cosmic dance, we are feeling the music. Since that first detection, LIGO and its European counterpart Virgo have heard the crashes of numerous black hole mergers, and even more stunningly, the collision of two neutron stars in 2017. That event produced both gravitational waves and a full spectrum of light, allowing telescopes around the world and in space to swivel and observe the same cataclysm, witnessing the creation of heavy elements like gold and platinum in the cosmic forge. This multi-messenger astronomy, combining the feel of gravity with the sight of light, is the ultimate fulfillment of the promise of that first detection. It has given us a new and powerful tool to probe the most extreme environments in the universe, to test the very laws of physics under conditions of unimaginable density and power, and to listen humbly to the deep, resonant chords of a cosmos that is far more dynamic and violent than we ever could have seen with our eyes alone. And just when we thought we understood the grand architecture of the cosmos, with its vast superclusters and flowing filaments of galaxies, astronomers stumbled upon a cavern of nothingness so immense it seemed to defy the very nature of the universe. This is the story of the Boötes Void, a cosmic desert whose staggering emptiness left scientists questioning the fundamental principles of how matter is distributed across space. The discovery process itself was a gradual, creeping realization. In the late 1970s and early 1980s, as astronomers like Robert Kirshner were conducting large-scale redshift surveys to map the universe in 3 dimensions, they noticed a perplexing gap in the constellation of Boötes. The data revealed a spherical region, a staggering 330 million light-years in diameter, where the pinpricks of light from distant galaxies simply vanished. It wasn't a complete vacuum, but the density of galaxies was so drastically low that it stood in shocking contrast to the crowded galactic metropolises found in superclusters. To put its scale into perspective, if our Milky Way were located at the center of the Boötes Void, we would not have discovered the existence of other galaxies until the 1960s, when our telescopes finally became powerful enough to peer beyond this unimaginable emptiness. The initial shock for cosmologists was profound. The prevailing model of the universe's large-scale structure, often called the cosmic web, suggested that matter should be distributed in a somewhat lumpy but generally consistent fashion. Vast filaments of dark matter were thought to shepherd galaxies into clusters and superclusters, leaving behind less dense regions known as voids. But these voids were typically expected to be on the order of 50 to 100 million light-years across. The Boötes Void was in an entirely different category. It was a void of such epic proportions that it seemed to break the model. Finding a region this empty was like discovering a hole in the ocean that was deeper than the Mariana Trench and wider than an entire continent. It challenged the cosmological principle, a foundational idea that, on sufficiently large scales, the universe should look roughly the same in all directions. The Boötes void was anything but uniform. It was a glaring, colossal anomaly that screamed for an explanation. The immediate scientific challenge was to figure out how such a void could possibly form. The leading theories of structure formation rely on tiny density fluctuations in the early universe, imprinted by the Big Bang. Over billions of years, gravity amplified these fluctuations, pulling matter into the dense regions that became galaxy clusters and leaving behind the emptier voids. But for a void as large as the one in Boötes to form through this process alone, the initial seed would have had to be anomalously underdense. Computer simulations of the evolving cosmos consistently struggled to produce voids of such scale and emptiness. This led to a period of intense debate and several thrilling, if speculative, hypotheses. One fascinating idea proposed that the Boötes void wasn't just an absence, but the result of a cosmic collision. The theory suggested that our observable universe might have collided with another, bubble universe in the distant past during a period of cosmological inflation, and the Boötes void is the scar or imprint of that staggering encounter, a region where the two universes failed to mix. While this remains a highly speculative idea, its very proposal highlights just how extreme and challenging this discovery was for conventional physics. As technology advanced, astronomers peered deeper into the void, and here they found a second, more subtle shock. The Boötes void is not completely empty. Scattered like lonely islands in this vast ocean of darkness, a few dozen galaxies have been found, but these isolated galaxies are themselves bizarre. Cut off from the constant gravitational interactions and galactic mergers that shape galaxies in clusters, they have evolved in profound isolation. They are often referred to as void galaxies, and they tend to be smaller, younger, and bluer than their cluster-dwelling counterparts with higher rates of star formation. They are essentially cosmic hermits, living out their lives in near-total solitude, their evolution dictated not by the bustling environment of a galactic city, but by the quiet, internal processes of a wilderness galaxy. The discovery of these isolated systems added a new layer to the mystery, transforming the void from a simple emptiness into a unique laboratory for studying galaxy evolution under the most extreme environmental conditions imaginable. The legacy of the Boötes void discovery is a lasting one. It served as a powerful and humbling reminder that our models of the cosmos, while incredibly powerful, are still approximations of a reality that is often far stranger and more complex. It forced cosmologists to refine their simulations and to accept that the cosmic web could contain structures of such extreme underdensity. The void taught us that nothing can be just as scientifically interesting as something, and that these vast empty regions play a crucial role in the overall dynamics of the universe, acting as the low-pressure zones that help drive the flows of galaxies along the dark matter filaments. The shock of its discovery wasn't just about finding a big hole in space. It was the realization that our universe is capable of producing patterns of emptiness on a scale that we, from our tiny vantage point, had never dreamed possible, a chilling and magnificent testament to the sheer, raw power of cosmic chance. From the profound emptiness of the Boötes void, we turn now to a discovery that points not toward a lack of something, but toward the gravitational pull of something entirely beyond our comprehension, something from outside the very universe we can see. This is the mind-bending mystery of the dark flow, a finding so controversial it suggests our entire cosmic neighborhood might be caught in a current flowing from a realm we can never observe. The story begins not with a single void, but with the meticulous study of the universe's largest gravitationally bound structures, galaxy clusters. These are the metropolises of the cosmos, enormous collections of hundreds or even thousands of galaxies, all held together by their mutual gravity and vast halos of dark matter. For years, scientists assumed that on the grandest scales, the motion of these clusters should be dominated by one thing and one thing only: the Hubble flow, the uniform expansion of the universe that carries all galaxies away from each other like raisins in an expanding loaf of bread. But in the early 2000s, a team of astronomers led by Alexander Kashlinsky decided to put this assumption to the test using a remarkable new dataset from the Wilkinson Microwave Anisotropy Probe, or WMAP, a spacecraft designed to map the faint afterglow of the Big Bang, the cosmic microwave background. They realized they could use this ancient light as a cosmic frame of reference. As galaxy clusters move through space, the hot gas trapped within them scatters the CMB photons, imparting a tiny shift in their energy known as the kinematic Sunyaev-Zeldovich effect. This shift is like a cosmic speed camera, revealing both the direction and the speed of a cluster's peculiar motion, that is, its motion relative to the overall expansion of the universe. By carefully analyzing the data for hundreds of distant clusters, the team expected to find these motions canceling each other out, a random, chaotic drift in all directions that would average to zero, perfectly in line with the cosmological principle. What they found instead was a collective gasp from the data. The clusters were not moving randomly. A significant number of them, stretching out across billions of light years, appeared to be streaming in a coherent direction, all heading toward the same specific patch of sky near the constellations Centaurus and Vela. This wasn't a small, local current. It was a vast, sweeping river of galaxy clusters, a coordinated motion on a scale so immense it seemed to defy the known gravitational influences of the entire observable universe. The team calculated that this streaming motion, which they termed the dark flow, was happening at a staggering speed of over 600 miles per second. The initial reaction from the cosmology community was a wave of profound skepticism, even shock. How could such a thing be possible? The gravitational pull from all the matter we can see, from the Great Attractor to the Shapley supercluster, was already accounted for, and it was nowhere near powerful enough to orchestrate this kind of coherent motion on such a colossal scale. It was as if every ship in an ocean, from coastliners to tiny dinghies, was being pulled by a hidden current whose source lay beyond the horizon. The most staggering and controversial implication of the dark flow is the potential source of this titanic pull. The leading hypothesis, the one that truly sends a shiver down the spine, is that this flow is being generated by the gravity of something that lies beyond our cosmic horizon, outside the observable universe. According to the standard Big Bang model, the observable universe is a finite sphere, about 93 billion light-years in diameter, containing all the matter and energy from which light has had time to reach us since the beginning. The dark flow, however, hints that the structure of reality is far grander. It suggests that the immense mass concentration tugging on our galaxy clusters is part of a larger cosmic structure, that inflation stretched far beyond our field of view. This could be another supercluster of unimaginable scale, or even an entirely different bubble universe in the wider multiverse, whose gravitational influence, unlike light, can somehow reach across the void and subtly shepherd the matter within our own cosmic bubble. If true, this would be the first ever empirical evidence for the existence of something beyond our observable universe, a ghostly hand from another realm guiding the motion of galaxies on a scale we are only just beginning to perceive. Of course, such an extraordinary claim has faced intense scrutiny and has been the subject of a fierce and ongoing scientific debate. Critics have pointed to potential systematic errors in the data analysis, suggesting that the measured signal could be an artifact of how the CMB map was cleaned and processed, or perhaps the result of unresolved foreground emissions from within our own galaxy. Subsequent studies using data from the Planck satellite, WMAP more sensitive successor, have produced conflicting results. Some analyses have failed to confirm the dark flow at the same significance, while others, including follow-up work by Kashlinsky's team using the Planck data, have claimed to not only confirm the original finding but to trace the flow out to even greater distances, suggesting its influence extends twice as far as initially thought. This lack of consensus is not a sign of failure, but rather a testament to how difficult it is to measure such a subtle effect at the very limits of our observational capabilities. The very struggle to confirm or refute the dark flow is a dramatic illustration of science in action, a high-stakes detective story playing out with the entire cosmos as its crime scene. Whether the dark flow is ultimately confirmed as a real phenomenon or fades away as a complex statistical illusion, its impact on cosmology has been profound. It has forced scientists to rigorously question the cosmological principle and to explore the extreme limits of our models. It has inspired a wealth of theoretical work, including investigations into whether the early universe's period of inflation could have left behind imprints in the form of such large-scale flows. The mystery challenges our most fundamental assumptions about the universe's symmetry and isolation. Are we living in a perfectly uniform, self-contained cosmic bubble, or are we merely one small part of a far vaster and more complex structure? A single tree in an infinite forest whose other trees we can never see, but whose shadow we might just be able to feel. The dark flow represents the ultimate frontier in astronomy, a hint that the greatest discoveries may not lie within the universe we can observe, but in the profound and invisible connections it may hold with realities beyond our own. Just when we think we have a handle on the chaotic beauty of stellar death, the universe unveils a structure of such precise geometry that it feels almost engineered, a cosmic piece of abstract art that left astronomers utterly bewildered. This is the story of the Red Rectangle Nebula, a celestial object that sounds more like a forgotten Mondrian painting than a dying star, and its discovery revealed a profound link between the violent end of stellar life and the very building blocks of our own existence. The initial shock came from its appearance. When astronomers first trained their telescopes on the star system HD 44179 in the constellation Monoceros, they were expecting to see the typical, messy splendor of a planetary nebula, the glowing, often spherical cloud of gas expelled by a sun-like star in its final death throes. Instead, they found something that defied all convention. A near-perfect X-shape, a series of concentric rectangles that appeared to be sketched onto the sky with a cosmic ruler and compass. The structure was so symmetrical, so unnaturally geometric, that it seemed to mock the chaotic, fluid dynamics that usually govern these stellar explosions. The mystery of its shape became an immediate obsession. How could a dying star produce such a crisp architectural form? The prevailing theory points to an unusual interaction within a binary star system at the nebula's heart. The aging red giant star isn't dying alone. It has a smaller, hotter companion star. As the red giant puffs away its outer layers, the smaller star's powerful gravitational influence doesn't just pull the gas away evenly. Instead, it funnels the ejected material into two opposing cones or jets that shoot out from the poles of the system. But the stars aren't stationary, they are precessing, wobbling like a spinning top that's starting to slow down. As this bipolar outflow spirals out into space, the precessing motion of the central stars paints the gas into that stunning, ladder-like series of rectangular rungs. The red rectangle isn't a static sculpture, it's a time-lapse photograph of a stellar wobble, a fossil record of a gravitational dance that has been choreographed over thousands of years. For scientists, the shock was in seeing such a clean, mathematical pattern emerge from one of the most turbulent and complex processes in stellar evolution, a perfect marriage of orbital mechanics and fluid dynamics that resulted in a masterpiece. Yet the greatest shock from the red rectangle wasn't its shape, but what it was made of. When astronomers performed a spectral analysis, breaking down its light into a chemical fingerprint, they discovered something even more staggering than its geometry. The deep red glow of the nebula, which gives it its name, wasn't just from the familiar emission of hydrogen gas. The spectrum was rich with the unmistakable signatures of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs. These are not simple molecules like water or carbon dioxide. PAHs are large, sturdy, carbon-based structures consisting of multiple benzene-like rings fused together. They are essentially the fundamental chicken wire-like skeletons of soot, but they are also considered to be crucial prebiotic building blocks. On Earth, similar molecules are thought to have played a role in the chemical pathways that led to the emergence of life. Finding them in the harsh, radiation-filled environment of a dying star system was a revelation that sent a jolt through the fields of astrochemistry and astrobiology. The implication was profound and humbling. It meant that the fundamental ingredients for life are not exclusive to the safe, warm ponds of young planets. The universe is a prolific chemist, forging these complex organic compounds in the most unlikely of places, in the turbulent outflows of dying stars, in the cold molecular clouds between the stars, and in the dusty disks around newborn suns. The discovery in the red rectangle provided a powerful piece of evidence for a concept known as panspermia, not in the sense of life itself traveling between stars, but in the sense of life's raw materials being ubiquitously seeded throughout the galaxy. The carbon and complex organics that eventually found their way to Earth via comets, asteroids, and interstellar dust could have been forged in stellar factories just like the red rectangle. This means that the very carbon in our DNA, the fundamental element of life as we know it, may have once been part of the beautiful, geometric funeral shroud of a long-dead star. The Red Rectangle Nebula, therefore, stands as a breathtakingly beautiful and shocking symbol of the cosmic cycle of death and birth, a place where the end of one stellar life provides the chemical seeds for the potential beginning of countless others. From the precisely timed wobble of the Red Rectangle, we now journey into a realm where time itself is warped to witness a pulse so regular it was thought to be impossible, the literal heartbeat of a black hole. We often imagine these cosmic monsters as the ultimate silencers, regions of pure chaos and destruction from which no rhythm or pattern could possibly emerge. Yet, in 2011, astronomers analyzing data from NASA's Rossi X-ray Timing Explorer satellite witnessed something that shattered this expectation. They were studying a stellar mass black hole named GRS 1915+105, located about 35,000 light-years away in our galaxy, as it fed on material siphoned from a nearby companion star. As this superheated gas spiraled inward, forming a furious, glowing accretion disk, the satellite recorded its X-ray emissions. What they found was not just random noise. There, buried in the furious roar of high-energy radiation, was a clear, steady, and repeating signal, a flicker that pulsed every 50 seconds with such metronomic precision that scientists could only describe it as the black hole's heartbeat. This phenomenon is known scientifically as a quasi-periodic oscillation, or QPO. The term quasi-periodic is key here because while the signal is remarkably stable, it isn't perfect like a crystal clock. It has a slight, measurable jitter that actually tells us more about the violent environment it comes from than a perfectly clean signal ever could. The initial shock for the research team was the sheer endurance of this heartbeat. It's one thing to see a brief, transient flicker in the chaotic maelstrom around a black hole. It is another thing entirely to observe that same rhythmic pulse continue, unwavering, for years on end. In the case of GRS 1915+105, this 50-second heartbeat was detected consistently across multiple observing runs, a testament to a stable, underlying physical process operating in the most extreme gravitational field imaginable. For a signal to persist for so long in such a violently dynamic region, just tens of miles from the point of no return, meant that scientists were looking at something fundamental, a cornerstone of physics playing out in real time. So, what could possibly be causing this rhythmic pulse so close to the event horizon? The leading explanation is as elegant as it is mind-bending, involving the very fabric of space-time itself. The theory points to a region of the inner accretion disk where the frenzied, superheated gas is no longer in a stable orbit, but is instead plunging inexorably toward its doom. In this final descent, just outside the event horizon, the particles are accelerated to nearly the speed of light, and the intense gravity creates what is known as a hotspot, a particularly dense and energetic clump of plasma. As this hotspot whips around the black hole on its final, fatal orbit, its immense speed and energy cause it to emit a powerful blast of X-rays. We see this as a flash. But because of a phenomenon called frame dragging predicted by Einstein's general relativity, the black hole's immense spin literally drags the fabric of spacetime around with it. This warped spacetime acts like a cosmic racetrack, forcing the hotspot into a specific preferred orbit. Every time this glowing clump of plasma completes a lap and returns to our line of sight, it flashes again, creating the rhythmic pulse we detect as the QPO. It's like a lighthouse beam sweeping across a dark ocean, but one where the lighthouse is anchored to the very edge of reality. The stability of this signal over years was the detail that truly left theorists stunned. It meant that the structures in the inner accretion disk, in this region of ultimate gravitational chaos, were far more organized and resilient than anyone had dared to predict. This wasn't a transient splash, it was a persistent, standing wave in the spacetime continuum, a resonant frequency of the black hole's gravitational field. The slight jitter in the timing of the pulses, the quasi-part of the oscillation, is now understood to be caused by vibrations within the accretion disk itself, much like the subtle variations in a musical note played on a vibrating string. By studying these tiny fluctuations, scientists can probe the properties of the accretion flow in a way that was previously impossible, measuring the black hole's mass and, crucially, its spin with incredible precision. This heartbeat, therefore, is not just a curiosity. It is one of the most powerful diagnostic tools we have for understanding the nature of black holes. It transforms them from abstract mathematical singularities into dynamic physical objects with measurable characteristics, allowing us to listen in as the universe plays its deepest, most fundamental rhythms on the strings of spacetime. While the rhythmic heartbeat of a black hole demonstrated the beautiful predictability of Einstein's cosmos, our next moment of shock emerged from a laboratory on Earth, where a team of engineers claimed to have built a machine that defied those very laws. This is the controversial saga of the M drive, a story that begins not with a cosmic discovery, but with a tantalizing and ultimately impossible promise. The concept was as simple as it was revolutionary: a truncated copper cone shaped like an empty ice cream cone enclosed in a vacuum chamber. When you pump microwave energy into this chamber, the photons bounce around inside, and according to the claims, something remarkable happens. The device experiences a tiny but measurable thrust in one direction. No fuel is burned, no propellant is ejected out of a nozzle, it simply pushes forward. This was the holy grail of propulsion, a reactionless drive, an engine that could theoretically generate thrust without needing to carry heavy fuel, making interstellar travel a practical possibility. The initial announcement sent a shockwave of excitement and disbelief through the aerospace community, because if it worked, it wasn't just a new kind of rocket. It was a machine that appeared to violate Newton's third law of motion, the fundamental principle that for every action there is an equal and opposite reaction. The allure of such a device is easy to understand. Every rocket we have ever built, from the tiny thrusters on a satellite to the colossal Saturn V that took humans to the moon, operates on the same brute force principle. Throw mass out the back end as fast as you can, and you will be pushed forward. This is the conservation of momentum in action, but that mass is propellant and it is incredibly heavy. To get a spacecraft to another star, you would need to carry an impossible mountain of fuel, making the journey utterly impractical. The M drive promised to shatter this limitation. A spacecraft equipped with such an engine could, in theory, accelerate continuously for years using only solar power or a small nuclear reactor to generate the microwaves, reaching a significant fraction of the speed of light without ever needing to refuel. It was the dream of science fiction made real, a technology that could fling open the doors to the solar system and beyond. The shock wasn't just the data, it was the intoxicating vision of a new age of space exploration that this single tabletop device seemed to offer. This intoxicating promise ignited a firestorm of intense scientific scrutiny. How could it possibly work? Proponents scrambled to offer theoretical explanations, often venturing into the fringes of known physics. Some suggested it was interacting with quantum vacuum fluctuations, a sea of virtual particles that pop in and out of existence. Others proposed it was creating a thrust against the very fabric of spacetime itself. The problem was that none of these explanations held up to rigorous mathematical scrutiny within the established framework of physics. To most physicists, the M-drive was no different from trying to make a car move forward by sitting in the driver's seat and pushing on the windshield. Without pushing against something external like the road, the car, and the M-drive shouldn't go anywhere, the scientific community was deeply divided. A handful of labs, including a team at NASA Eagleworks Laboratory, reported that they, too, had measured a small, anomalous thrust in their own M-drive experiments. These results, published in lower-tier journals, kept the hope alive. Meanwhile, the vast majority of physicists remained profoundly skeptical, convinced that the measured thrust was not evidence of new physics, but of hidden, mundane experimental errors. The quest for the truth led to a multi-year, global effort to either validate or debunk the M-drive once and for all. The challenge was that the claimed thrust was infinitesimally small, equivalent to the weight of a single grain of sand. At this minute scale, dozens of subtle effects could masquerade as a false positive. Could it be heating from the microwaves causing the device to expand and subtly push against the test stand? Was it the Earth's magnetic field interacting with electrical currents in the wires, or was it an artifact of the vacuum chamber itself? The most dedicated skeptics argued that if the M-drive truly worked, it would not only revolutionize space travel but overturn 3 centuries of classical mechanics. Extraordinary claims, as the saying goes, require extraordinary evidence, and the evidence for the M-drive was frustratingly fragile and inconsistent. Different labs got wildly different results, and the thrust seemed to change direction depending on how the device was oriented, a telltale sign of an interaction with the local environment, not a genuine propulsion effect. The final, definitive shock came from the most meticulous test of all, conducted by a team at the Dresden University of Technology in Germany. They built a super-sensitive thrust balance housed in a vacuum chamber and designed it with one primary goal: to eliminate every possible source of error that had plagued previous experiments. Their apparatus was so sensitive it could measure forces down to a few dozen nanonewtons. They ran the M-drive, and initially they too saw a tiny thrust signal. But then they performed the crucial, controlled experiment. They ran the test again, but this time they rotated the entire apparatus. If the thrust was genuine and coming from the M-drive itself, the direction of the push should have rotated with the device. Instead, the thrust signal remained fixed in the lab's reference frame. It was pointing toward a specific direction in the room, completely independent of which way the drive was facing. This was the smoking gun. The thrust wasn't coming from the magical interaction of microwaves in a copper cone. It was coming from the interaction of the power cables feeding the device with the Earth's magnetic field. The tiny force they were measuring was a simple magnetic Lorentz force, a well-understood phenomenon from the 19th century. The impossible thrust was an illusion, a subtle, stubborn artifact that had fooled researchers for nearly 2 decades. The debunking of the M-drive was a profound lesson in the essential, self-correcting nature of science. It was a story that showcased both the power of a beautiful, revolutionary idea and the even greater power of rigorous, skeptical investigation. The initial shock of its potential gave way to the more sobering but equally important, shock of realizing how easy it is to be deceived by our own instruments and our own hopes. The M drive did not open the door to the stars, but it did reaffirm a fundamental truth. The laws of physics are not easily broken. They are resilient, tested, and foundational. While the dream of a reactionless drive remains just that, a dream, the meticulous process that exposed the M drive's flaws stands as a testament to the scientific method's relentless pursuit of truth, a process that is often messy, contentious, and slow, but one that ultimately guards us from building our future on a beautiful but impossible illusion. Yet for all the violent cosmic crashes we can hear with gravitational waves and see with telescopes, there are messengers from these events that are far more elusive, so shy they can pass through a light year of solid lead without a single interaction. These are neutrinos, the universe's ultimate ghosts, and for decades detecting their cosmic origins felt like a nearly impossible dream. Every second, trillions of these subatomic phantoms stream through your body, coming from our sun, from radioactive decay in the Earth, and from cataclysms in the distant universe. But because they barely interact with normal matter, catching one is like trying to grab a specific snowflake in a blizzard using a butterfly net. For a century, high-energy neutrinos from deep space had no identifiable home. They were a diffuse, anonymous rain, a cosmic background noise with no story to tell. All of that changed in a single, breathtaking moment in September of 2017, when a single ghost particle arrived from the depths of space and pointed a definitive finger back at its monstrous source. The detective in this story is the Ice Cube Neutrino Observatory, one of the most audacious scientific instruments ever conceived. It isn't a traditional telescope with a glass lens or a metal dish. Instead, it's a colossal cube of perfectly clear Antarctic ice, 1 kilometer on each side, buried deep beneath the surface at the South Pole. Embedded within this frozen expanse are over 5,000 ultra-sensitive light detectors, strung along 86 cables that dangle into the ice like the strings of a colossal harp. The entire setup is designed to do one thing: wait. It waits for the 1 in a trillion chance that a high-energy neutrino from deep space will actually interact with an atom in the ice. When that happens, it produces a faint subatomic shockwave of blue light known as Cherenkov radiation. By meticulously tracking the precise timing and intensity of this blue light as it passes through the grid of sensors, Ice Cube supercomputers can reconstruct the neutrino's energy and, most importantly, the exact direction from which it came. It is a telescope that uses the entire planet Earth as a shield, blocking out all other cosmic rays to stare into the void with a lens made of pure ice. On September 22, 2017, the wait paid off. The observatory's automated alert system was triggered by a single, spectacular event. A neutrino with a staggering energy of about 290 tera-electronvolts had slammed into the ice. This was no ordinary solar neutrino. This was a cosmic bullet carrying the energy of a major league fastball, and it had traveled across the universe to reach us. This specific neutrino was given the rather unpoetic name Ice Cube 170922A, but its importance was anything but mundane. Within minutes of the detection, an automated alert was sent out to observatories around the world, providing the coordinates of the patch of sky the neutrino had come from. The race was on to see what was there. Telescopes across the globe and in space immediately swiveled to stare at that location. Among them was the Fermi Gamma Ray Space Telescope, which had been monitoring the sky for high-energy gamma rays for nearly a decade. In its archival data, scientists found something remarkable. For months, a known object in that exact part of the sky had been in a state of extreme activity. It was a blazar, a monster known as TXS 0506+056, located about 4 billion light-years away in the constellation Orion. A blazar is one of the most violently energetic objects in the entire cosmos. It is a supermassive black hole, millions or even billions of times the mass of our Sun, sitting at the center of a distant galaxy. What makes a blazar special is that it is actively feeding, pulling in vast amounts of gas and dust, and in the process, it fires out twin jets of radiation and subatomic particles at nearly the speed of light. We on Earth just happen to be looking almost directly down the barrel of one of these jets, making it appear incredibly bright and variable. The Fermi data showed that this particular blazar had been in a furious outburst, its gamma-ray flux dramatically elevated at the very time the neutrino arrived. Further observations from the magic atmospheric Cherenkov telescopes in the Canary Islands confirmed an intense flare of very high-energy gamma rays from the same source. The correlation was undeniable. For the first time in history, scientists had done the impossible. They had traced a single high-energy neutrino back to its specific cosmic accelerator, a raging, supermassive black hole 4 billion light-years away, firing a jet of particles directly at Earth. The implications of this discovery sent a shockwave through astrophysics that was every bit as profound as the first detection of gravitational waves. This was the birth of a fully realized multi-messenger astronomy. No longer were we limited to observing the universe just with light or just with gravitational waves. Now we could combine them with this third, ghostly messenger. The neutrino was the smoking gun, the direct evidence that blazars are not just sources of light, but powerful natural particle accelerators, capable of producing the most energetic neutrinos and cosmic rays. It confirmed a century-old hypothesis about the origins of these mysterious high-energy particles that constantly bombard our atmosphere. The deeper shock, however, was what this told us about the incredible engines at the hearts of these distant galaxies. To produce a neutrino of such immense energy, the conditions inside the blazar's jet must be almost unimaginably violent. The prevailing theory is that protons, accelerated to near light speed within the jet, collide with other particles or photons, creating a cascade of secondary particles, including pions, which then decay to produce both the high-energy neutrinos and the gamma rays that were observed simultaneously. We were essentially witnessing the inner workings of a cosmic cannon, a natural accelerator far more powerful than anything we could ever build on Earth. This single detection did more than just identify a source. It unveiled a fundamental mechanism of the universe, a process by which the most massive objects in existence can fire fundamental particles across billions of light years, turning them into detectable messengers that carry secrets from the very heart of the chaos. It was a stunning reminder that even the most elusive ghosts in the cosmos, if we are patient and clever enough to catch them, can tell us the most vivid and explosive stories about the universe's most extreme phenomena. But for all the worlds we've discovered made of rock and gas and ice, nothing could have prepared astronomers for a planet that seemed to be crafted from one of the universe's most precious treasures. The star system 55 Cancri, located about 40 light-years away in the constellation Cancer, had long been known to host a family of planets. But one member of this family, the innermost world known as 55 Cancri E, stood out as profoundly bizarre. Initial studies classified it as a super-Earth, a type of planet with a mass greater than our own but substantially less than the ice giants Uranus and Neptune. As scientists refined their measurements, they calculated its mass to be about 8 times that of Earth and its radius to be nearly twice as large. This relationship between mass and size is a critical clue to a planet's composition. A world made mostly of rock and iron like Earth will have a certain density. A world rich in lightweight gases like hydrogen and helium will be much larger and less dense for the same mass. But 55 Cancri E fit neither profile. It was far too massive for its size, indicating an incredibly dense material was crammed into that relatively small volume. The shocking realization came when astronomers turned their attention to the planet's host star. 55 Cancri A is a star notably richer in carbon than it is in oxygen. In a planetary system, the building blocks available come directly from the composition of the primordial cloud that formed the star. Around a carbon-rich star, the fundamental chemistry of planet formation changes dramatically. Instead of silicates and water ice dominating the construction of rocky worlds, you would expect carbon compounds to take center stage. In such an environment, a planet forming close to the star, where temperatures are too high for lightweight gases to be retained, could very well condense from a soup rich in carbon. Theoretical models suggested that under the immense pressures and scorching temperatures expected on 55 Cancri E, with a surface temperature potentially exceeding 2,100 degrees Celsius, the carbon within the planet would be forced into a crystalline structure. In other words, a significant portion of the planet's interior, perhaps up to a third of its entire mass, could quite literally be diamond. Imagine a world utterly alien to our own, a landscape that defies earthly geology. This is not a planet of mountains and oceans, but a glittering, dark jewel orbiting perilously close to its sun. The surface itself might be a vast graphite plain, slick and dark, but as you journey deeper into the planet, the pressure would transform that graphite into a thick layer of diamond, forming a mantle of gemstone hundreds of miles thick. There would be no tectonic activity as we know it, no volcanic eruptions of molten rock. Instead, the planet's geology would be driven by the strange properties of its carbon-based composition. Some scientists have even speculated that under the right conditions, carbon silicate volcanoes could erupt, spewing a strange, tar-like lava. The very rain on this world, if any atmosphere could persist in the blistering heat, would not be water but potentially liquid carbon compounds. The discovery sent a jolt through the planetary science community, not just because of its novelty, but because it represented a completely new class of planet, one whose very existence was predicated on a carbon-dominated chemistry we have no direct experience with on Earth. Of course, the initial diamond planet hypothesis was met with both excitement and healthy scientific skepticism. Subsequent observations have painted a more complex and in some ways even more baffling picture. Studies of the planet's thermal emissions revealed another staggering surprise. 55 Cancri E appears to have a wildly fluctuating temperature. One side of the planet is tidally locked, perpetually facing its star, and should be consistently, unimaginably hot. Yet measurements showed that the hottest spot on the planet isn't directly under the star's glare, but is shifted significantly to one side. This suggests the planet might not have a global atmosphere that efficiently redistributes heat, but perhaps a transient one violently vented from a still molten interior. Other theories propose that the planet is shrouded in a thick, hazy atmosphere of vaporized rock and carbon, creating a global, superheated fog. The possibility remains that the diamond interior is real, but hidden beneath a dynamic and hellish surface that is constantly being reshaped by the extreme energies at work. The true shock of 55 Cancri E, therefore, is not just that a diamond planet might exist, but that it forces us to expand our imagination of what is possible. It reveals a universe of planetary diversity far beyond the simple categories of terrestrial and gas giant, showing us worlds can be forged from the very elements we value most, creating landscapes of almost mythic extravagance in the crucible of alien suns. But just when we think we've seen the universe's most extreme velocities, a discovery emerges that redefines the very meaning of speed, revealing a stellar corpse hurtling through the galaxy like a cosmic bullet fired from an immense celestial gun. This is the story of the Cannonball Pulsar, officially known as PSR J0002+6216, a pulsar that wasn't just spinning rapidly, it was flying through the void at a pace so breathtaking it left astronomers struggling to comprehend the forces that could have possibly launched it. A pulsar is the crushed, ultra-dense core of a massive star that has died in a supernova explosion. When such a star exhausts its nuclear fuel, its core collapses under its own immense gravity, crushing protons and electrons together to form a city-sized sphere of neutrons so dense that a single teaspoon of its material would weigh billions of tons on Earth. As this neutron star forms, it conserves the original star's angular momentum, causing it to spin up to incredible speeds, often hundreds of times per second. It also amplifies its magnetic field to a strength 1,000,000,000,000 times greater than Earth's. The combination of rapid rotation and a powerful magnetic field creates a lighthouse-like effect, beaming out intense radiation from its magnetic poles. If one of those beams happens to sweep across Earth, we detect it as a regular, repeating radio pulse, hence the name pulsar. Most pulsars drift through space at a few 100,000 miles per hour, a respectable speed, but not one that typically raises alarms. The Cannonball pulsar, however, was in a league of its own, discovered by a citizen science project called Einstein at Home, which uses the idle processing power of volunteers' computers to sift through vast amounts of astronomical data. This particular pulsar immediately stood out. When scientists calculated its velocity, the result was staggering. It was racing through space at nearly 2.5 million miles per hour. To put that incomprehensible speed into perspective, at that velocity you could travel from Earth to the Moon in just under 6 minutes. This object was moving so fast that it wasn't just drifting. It was escaping the gravitational pull of our entire Milky Way galaxy, destined to become a lone wanderer in the intergalactic void. The initial shock of its speed was soon eclipsed by an even more dramatic visual discovery. When astronomers examined radio telescope images of the region, they saw something that took their breath away. The pulsar wasn't just a lonely point of light. It was positioned like a bullet at the very tip of a colossal, spear-like tail of energized particles and cosmic rays. This tail, glowing brightly in radio waves, stretched back across space for an incredible 13 light-years. To visualize that, imagine a trail of cosmic debris so long it would take light itself 13 years to travel from one end to the other, a path pointing directly back to the scene of the crime. This tail was created by the pulsar's powerful, gusting wind of charged particles slamming into the thin, scattered gas of interstellar space as it plowed through it at phenomenal speed. The resulting shock wave energizes the particles, causing them to emit radio waves and creating a brilliant, arrow-straight pointer that leaves no doubt about the pulsar's trajectory or its astonishing velocity. This cosmic arrow, however, was pointing directly at the heart of another mystery. At the far end of that 13 light-year-long trail lay a supernova remnant known as CTB-1. A supernova remnant is the expanding shell of debris left over from the titanic explosion that created the pulsar in the first place. The geometry was undeniable and deeply shocking. The Cannonball pulsar had not only been born in that explosion, but had been launched from it with such an unimaginable kick that it had already completely overtaken and escaped the outer edge of the expanding debris cloud. It was now far out in front, a runaway projectile that had left its own birthplace far behind. This observation sent theorists scrambling back to their supernova models. Standard supernova explosions are thought to be roughly symmetrical, with the outer layers of the star blowing off in a more or less spherical shell. A symmetric explosion might give the newborn neutron star a modest nudge, but it could never account for the cannon-like launch that propelled PSR-J0002. To achieve such an extreme velocity, the supernova must have been profoundly lopsided, a catastrophic detonation where the explosion was vastly more powerful in one direction than in all the others. The leading theory to explain this is rooted in the chaotic physics of a dying star's final moments. As the core of a massive star collapses, it can become a raging maelstrom of turbulent matter and neutrinos. In this ferocious environment, it's possible for sloshing waves of material and incredible pressure imbalances to develop deep within the collapsing core. If these instabilities are strong enough, they can focus the energy of the explosion into a powerful jet, erupting from one pole of the dying star like a thrust nozzle on a rocket. The newborn neutron star would be the recipient of the opposite and equal reaction, kicked violently in the opposite direction. It's the ultimate cosmic recoil, as if the universe itself had fired a rifle, with the supernova remnant being the expanding cloud of gunpowder smoke and the pulsar being the high-caliber slug rocketing downrange. The cannonball pulsar provides the most compelling visual evidence ever found for this asymmetric explosion model, a smoking gun for stellar death that is anything but a serene, symmetric fade-out. It reveals that the death of a star can be a chaotic, violent, and staggeringly powerful event, capable of forging a dense stellar corpse and then firing it across the galaxy like a champion from a cosmic slingshot, forever marked by the violent, one-sided nature of its spectacular birth. Sometimes the greatest discoveries aren't about finding something new, but about finding something old that we had given up for lost, a forgotten piece of technology that, when recovered, can suddenly tell us more than we ever imagined. This is the remarkable story of the little Soviet rover that refused to be forgotten, and how a decades-old relic on the moon became one of the most valuable tools for testing the fundamental laws of the universe. In the heat of the space race, the Soviet Union achieved what was then an astonishing feat of engineering. They landed the first remote-controlled rovers on the lunar surface. Lunokhod 1 touched down in November of 1970, a sophisticated 8-wheeled vehicle equipped with cameras, soil testing equipment, and a crucial, yet seemingly simple, instrument on its deck, a French-built laser reflector array. This device, known as a corner cube reflector, is a masterpiece of precision. It's designed to act like the ultimate cosmic road sign, reflecting any laser beam fired from Earth directly back to its point of origin with incredible accuracy. For almost a year, Lunokhod 1 trundled across the Sea of Rains, sending back data, until finally, in September of 1971, it fell silent, its location lost and its reflector abandoned to the lunar dust. For the next 4 decades, the Lunokhod 1 reflector was a ghost. Scientists continued to use other reflectors left on the moon by the Apollo 11, 14, and 15 missions, as well as the one on the still-functioning Lunokhod 2. These experiments, known as lunar laser ranging, became a cornerstone of modern physics. By firing powerful laser pulses from observatories on Earth and timing how long it takes for the faint photon to return, a journey of roughly 2.5 seconds each way, researchers could measure the distance between the Earth and the Moon with an accuracy of a few millimeters. This incredible precision allowed for breathtaking tests of Einstein's theory of general relativity, confirming predictions about the Moon's orbit with stunning fidelity, and even allowing us to study the Moon's subtle wobble to probe its liquid core. But the loss of Lunokhod 1 was a persistent annoyance. It was one more data point that could improve the statistical accuracy of these measurements, a missing piece of the puzzle just sitting there in the lunar regolith, waiting to be found. The breakthrough came from an unexpected source, NASA's Lunar Reconnaissance Orbiter, which began mapping the Moon's surface in exquisite detail in 2009. Armed with high-resolution camera images, a team of researchers led by physicist Tom Murphy from the University of California, San Diego, went on a cosmic treasure hunt. They pored over the LRO images, searching the vast, flat expanse of the Sea of Rains for a tiny, long-dead rover. It was a monumental task, like looking for a lost coin on a beach from thousands of miles away. But their persistence paid off. They spotted it, a faint, bright speck that was the sun glinting off the dormant Lunokhod 1. They had a location, but the real question remained. After 40 years of exposure to the brutal extremes of lunar temperature and constant micrometeorite bombardment, was the reflector even still functional? Could it possibly still reflect a laser beam after all this time? On April 22, 2010, the team at the Apache Point Observatory in New Mexico decided to find out. They aimed their powerful laser at the newly calculated coordinates and fired a series of pulses toward the Moon. Then they waited, their detectors poised to catch the faintest glimmer of a returning signal. The initial attempts yielded nothing. It was like shouting into a canyon and hearing only silence in return. But they refined their aim, accounting for tiny gravitational perturbations in the laser's path, and tried again. And then it happened. A few precious photons, the unmistakable signature of a clean reflection, returned to the telescope. The signal was weak, but it was unmistakable. Against all odds, the long-lost Lunokhod 1 reflector was not only still there, but it was working perfectly, and it was talking to Earth once more. The shock and elation in the control room was palpable. They had just resurrected a piece of space history, and in doing so, they had unlocked a powerful new tool for science. The rediscovery was far more than a sentimental victory. It turned out that the Lunokhod 1 reflector had a secret superpower. Due to its specific location on the Moon, it became, by a significant margin, the best reflector of the entire set. It returns signals to Earth up to 5 times brighter than the Apollo 15 array, its corner cubes seemingly pristine despite their long slumber. This powerful signal has supercharged the field of lunar laser ranging. The newfound precision is allowing for even more stringent tests of general relativity, probing such subtle effects as the strong equivalence principle, the idea that gravity accelerates all objects at the same rate, regardless of their composition or binding energy. By measuring the Moon's orbit with this new millimeter-level precision, scientists can check if the Earth and Moon fall toward the Sun at exactly the same rate, a test that could reveal tiny cracks in Einstein's theory and point the way toward a deeper understanding of how gravity works. Furthermore, the consistent, high-quality data from Lunokhod 1 is giving us an unprecedented look inside the Moon itself. By analyzing the tiny librations or wobbles in the Moon's rotation, physicists can infer the nature and size of its liquid core, determining whether it is a solid ball or a molten shell, and thus unraveling the thermal history and evolution of our closest celestial neighbor. A Soviet machine, lost and forgotten for a generation, had been reborn as a vital instrument for 21st century physics, a humble reflector that continues to shine a light on the deepest mysteries of gravity, time, and the very structure of our cosmic companion. And just when we thought our solar system had surrendered its final giants, a digital phantom emerged from a decades-old archive of data, a slow-moving speck that would soon be recognized not as just another comet, but as a behemoth from the deepest, darkest freeze of our cosmic backyard. This is the story of Comet Bernardinelli-Bernstein, a discovery that redefined the upper limits of what a comet could be and sent a jolt of pure astonishment through the planetary science community. The initial discovery was a masterclass in modern astronomical archaeology. In 2021, astronomers Pedro Bernardinelli and Gary Bernstein were painstakingly sifting through data from the Dark Energy Survey, a project that had spent years mapping distant galaxies to study the universe's accelerating expansion. But within that colossal dataset containing billions of faint points of light, they were hunting for something much closer to home: distant, slow-moving trans-Neptunian objects. Using sophisticated algorithms to identify objects that shifted position from image to image, they pinpointed a faint, slow-moving dot that had been captured in the survey's images years earlier, its motion so gradual it had previously gone unnoticed. The initial designation was unassuming, but as astronomers around the world turned their largest telescopes toward this new object, the initial measurements triggered a wave of disbelief. Its brightness was staggering for something so incredibly far away. Comets are typically a few kilometers across, but the reflected sunlight from this object, even from the chilly depths beyond Neptune, indicated a nucleus of almost incomprehensible scale. Refined calculations revealed that Comet Bernardinelli-Bernstein, or C 2014 UN-271, was not a mere 10 or 20 kilometers wide. Its nucleus was estimated to be between 100 and 200 kilometers in diameter, To put that in perspective, this single comet's icy core is larger than the state of Rhode Island and contains more mass than every other comet we've ever observed combined. It is, by a colossal margin, the largest comet humanity has ever laid eyes on. The shock wasn't just its size, but the realization that such a monster had been lurking in our own solar system all this time, completely unknown to us until a dedicated digital search fished it out of a sea of ancient starlight. The object's origin story is just as shocking as its dimensions. Its immense, looping orbit is a dead giveaway that it is a pristine visitor from the Oort cloud, a theoretical shell of icy leftovers that surrounds our solar system like a distant, frozen vault. This isn't the closer in Kuiper belt, where Pluto and other dwarf planets reside. The Oort cloud is a realm of almost mythical distance, a cloud of trillions of icy bodies that begins roughly 2,000 times farther from the Sun than Earth and stretches perhaps halfway to the next star. Comet Bernardinelli-Bernstein is a messenger from this ultimate frontier, and its current journey inward is not a frequent one. Its orbital period is measured in millions of years. The last time it visited the inner solar system, early human ancestors were just beginning to walk upright on the African savanna. This immense travel time is what makes it so scientifically precious. Unlike comets from the Kuiper belt that have been periodically warmed and altered by the Sun, this megacomet has spent nearly its entire existence in the deep freeze of interstellar space, at temperatures just a few degrees above absolute zero. This profound isolation means its composition is a perfect frozen time capsule from the solar system's very dawn. Locked within its 150-kilometer wide core is a perfectly preserved sample of the primordial material from which our entire planetary system formed 4.5 billion years ago. While other comets have been baked and changed by repeated solar encounters, losing their most volatile ices, Bernardinelli-Bernstein is thought to be in a state of perfect chemical arrest. It is a block of pure history containing the original ices, dust, and organic molecules that were the building blocks of the planets. As it makes its slow, stately journey toward the inner solar system, it offers astronomers a once-in-a-lifetime, or rather once-in-a-species, opportunity to study the raw ingredients of our cosmic origins in their most unspoiled state. Its approach is not a threat. It will come no closer to the Sun than the orbit of Saturn around the year 2031, but a grand celestial presentation, a chance to point our most powerful telescopes, like the James Webb, at a relic that has been untouched since the Sun itself was a newborn star. The discovery of this icy leviathan is a humbling reminder that even in our own neighborhood, we are still capable of finding true giants, and that the deepest secrets of our origin are still held in the silent, slow-moving wanderers of the dark. But perhaps the single greatest shock, the one that has most fundamentally rewritten our place in the cosmic story, didn't come from a single bizarre object or a fleeting signal. It came from a statistical revolution. A quiet, methodical census of the stars that revealed our galaxy is not a lonely expanse but a teeming ocean of worlds. For centuries, the very existence of planets around other stars was a subject of pure philosophical speculation. We had our one example, our own solar system, and no proof that any others existed. The question of whether we were alone was in many ways premature because we didn't even know if there were other places for life to be. All of that changed with the launch of the Kepler Space Telescope in 2009. A mission that would transform a cosmic question mark into a staggering, undeniable exclamation point. Kepler's strategy was as simple as it was brilliant. It stared unblinkingly at a single patch of sky containing over 150,000 stars, its sensitive photometer measuring their brightness with incredible precision. It was looking for the telltale sign of a transiting planet, that faint, periodic dip in a star's light caused when an orbiting world passes directly in front of it, blocking a tiny fraction of its brilliance. This transit method is like detecting a gnat flying in front of a searchlight from thousands of miles away. It requires perfect alignment and immense patience. Kepler's mission was to provide that patience, gathering data for years to catch these incredibly subtle, repeating winks. The initial hope was that it might find a handful of Earth-sized planets. What it delivered instead was a fire hose of data that completely overwhelmed our old, solitary view of the cosmos. The first wave of shock was the sheer, overwhelming number. As the data was analyzed, the exoplanet count didn't just climb, it exploded. Kepler revealed that planets are not the exception, they are the rule. The statistics that emerged were nothing short of mind-boggling. The data suggested that, on average, every star in the sky likely hosts at least one planet. Given the hundreds of billions of stars in our Milky Way galaxy, this simple statement implies the existence of trillions of planets in our galaxy alone. Imagine that for a moment. The vast, dark spaces between the stars that we look up at on a clear night are not empty. They are filled with an unimaginable multitude of worlds, gas giants, ice giants, rocky spheres, and planets of types we don't even have in our own solar system. Our familiar collection of 8 planets went from being a presumed standard to being just one possible configuration in a universe of seemingly infinite variety. The cosmos, Kepler showed us, is fundamentally a place of planets, yet the second and even more profound shock was the location of so many of these worlds. Kepler's primary goal was to find planets in the habitable zone, that Goldilocks region around a star where the temperature is just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. Liquid water is the one non-negotiable ingredient for life as we know it, the universal solvent for the chemical reactions that make biology possible. Before Kepler, we had no idea how common such worlds might be. Was Earth a 1 in a trillion fluke? The answer from the data was a resounding no. Kepler discovered thousands of planets orbiting within their star's habitable zone. These weren't just gas giants, many were rocky worlds similar in size to Earth, tantalizingly dubbed Earth cousins or super-Earths. The most iconic of these is perhaps Kepler 452b, a world orbiting a star very similar to our own Sun at a distance that places it squarely in that life-friendly region. Suddenly, the potential for Earth-like conditions was not a rare cosmic privilege, but a common feature of the galactic landscape. This statistical revolution fundamentally altered the Drake equation, the famous framework for estimating the number of communicative civilizations in the galaxy. One of the most critical terms in that equation was always the biggest unknown, the fraction of stars that have planets and the fraction of those planets that are habitable. Kepler provided a stunningly optimistic answer. It told us that the first few terms of the equation are likely very large, with so many stars and so many planets orbiting them, and a significant fraction of those in the habitable zone. The sheer number of potential incubators for life in our galaxy is astronomically high. The shift in perspective was monumental. The question is no longer if there are other Earth-like worlds, but how many there are and what kind of life they might host. We went from wondering if we were the only oasis in a vast desert to realizing we are most likely standing in a cosmically dense rainforest, surrounded by a canopy of countless other worlds, each with its own story, its own environment, and its own potential for wonder. The legacy of the Kepler mission's great census is a humbling and thrilling paradox. By revealing the staggering commonality of planets, it made our own Earth feel both incredibly special and profoundly ordinary at the same time. It is special because it is our home, the one world where we know for certain the miracle of life has occurred. Yet it is ordinary in the sense that the physical processes that formed it, the accretion of dust in a protoplanetary disk, the delivery of water by comets, the orbital dynamics that placed it in the habitable zone, appear to be happening everywhere we look. The universe, it seems, is a master planet builder, and the ingredients for life appear to be standard issue. This doesn't guarantee that life is out there, but it demolishes the argument that the conditions for it are rare. The great exoplanet boom gave us the ultimate statistical shock. We live in a universe that is not just capable of creating worlds like our own, but one that seems to do so with prodigious, extravagant abundance, inviting us to finally ask the oldest question with a new, evidence-based sense of awe and profound possibility. What an incredible journey through the cosmos we've just taken together. From the ghostly presence of black holes made visible to the fleeting, tantalizing whisper of the WOW signal, from the gentle, mysterious push on the Pioneer probes to the accidental discovery of the Big Bang's own echo, we have witnessed 25 moments where the universe looked the world's top scientists square in the eye and said, "Think again." Each of these shocks, whether it was the baffling acceleration of the universe driven by dark energy, the haunting possibility of water, and maybe even life on Mars, or the geometric perfection of the Red Rectangle Nebula, has served as a powerful reminder that our models and theories are not the final word, but merely the latest draft in an ongoing, billion-year-old conversation with reality. These weren't just minor adjustments to a data set. They were fundamental ruptures in our understanding, moments that forced us to tear out whole chapters of the textbooks and start writing new ones, filled with wonder and a renewed sense of humility. The true legacy of these discoveries is not simply a longer list of facts about the cosmos. It's a profound shift in our perspective. We've learned that our solar system is not the neat, orderly family of 8 we once thought, but may harbor a hidden giant in Planet 9, and that it is visited by bizarre interstellar travelers like Oumuamua. We've discovered that our galaxy is not drifting serenely in the cosmic flow, but is being pulled by immense, unseen structures like the Great Attractor, and perhaps even by influences from beyond our observable universe in the dark flow. We have opened our ears to the symphony of the cosmos, hearing the chirp of colliding black holes through gravitational waves and feeling the steady heartbeat of a black hole's hotspot. We have even found that the very ingredients for life are forged in the violent deaths of stars, and that worlds of diamond and cities of comets exist in numbers so vast they defy human comprehension. Every single one of these revelations pushes the boundary of what we thought was possible, revealing a universe that is not only stranger than we imagine, but stranger than we can imagine. This relentless, beautiful strangeness is the engine of science itself. It is the driving force behind every telescope pointed at the sky and every equation scribbled on a chalkboard. It is the reason we keep looking, keep listening, and keep questioning. The universe is the greatest mystery novel ever written, and with every shocking discovery, we turn a page, only to find that the plot has thickened in ways we never saw coming. So now we turn this conversation over to you. As you look up at the night sky with these new wonders swirling in your mind, we have to ask, which of these 25 moments left you the most utterly stunned? Was it the thought of that colossal, buried lake on Mars, a potential sanctuary for alien life? Was it the spine-tingling possibility of a Dyson sphere being built around a distant star? Or was it the simple, profound statistic that our galaxy alone is likely home to trillions of planets? Let us know your thoughts in the comments below. We are genuinely excited to hear which cosmic surprise resonated most deeply with you. And if you're hungry for more deep dives into the universe's greatest mysteries, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the unknown. The cosmos is full of secrets waiting to be uncovered, and the next great shock is always just one observation away.